65 million years ago, something came hurtling from the darkness at the edge of our solar system and nearly erased all life on Earth. It wasn't an asteroid. It was a comet, a frozen time bomb from a mysterious graveyard of ice and rock that surrounds us right now, called the Oort Cloud. And here's what terrifies scientists. That cloud holds millions of these objects. Any one of them could be nudged toward Earth without warning. But now, NASA has discovered something even more disturbing emerging from that ancient frozen wasteland, a megacomet. So massive, it dwarfs the one that ended the dinosaurs, and it's showing signs of activity that shouldn't be possible. If mind-bending cosmic secrets keep you up at night, smash that like button and subscribe, because what I'm about to show you will redefine everything we thought we knew about the edge of our solar system. Prepare yourselves. We begin. The Oort Cloud is one of the most mysterious and haunting structures in our entire solar system. Yet most people have never heard of it. And for good reason, because it has never been directly observed by any telescope. No spacecraft has ever reached it, and it exists so far beyond anything we consider familiar that it challenges our very understanding of where our solar system actually ends. To put this in perspective, when you think about the solar system, you probably picture the sun at the center with 8 planets orbiting around it. Maybe you think of the asteroid belt between Mars and Jupiter, or perhaps you remember Pluto out there in the cold darkness. But the Oort Cloud makes all of that look like it's practically sitting in the sun's lap. The inner edge of the Oort Cloud begins somewhere around 2,000 times farther from the sun than Earth is, which means if you could somehow travel at the speed of light, it would take you about 11 days just to reach the beginning of this mysterious region. And that's more than 50 times farther away than Pluto, which already sits at such an incredible distance that it takes sunlight over 5 hours to reach its frozen surface. The Oort Cloud is believed to be a massive spherical shell, not a flat disk like the planets orbit in, but an actual sphere completely surrounding our entire solar system like a bubble. And this bubble is filled with trillions of icy objects, ranging from the size of mountains to chunks, no larger than a boulder, all drifting in the cold darkness at the very edge of where the sun's gravity can still hold on to them. Scientists estimate there could be as many as 1 trillion objects in the Oort Cloud, which is more than all the stars in the entire Milky Way galaxy. And these aren't just random space rocks, they're ancient, primordial material left over from the violent birth of our solar system 4.6 billion years ago. Frozen time capsules that have remained essentially unchanged since the days when the planets were first forming. The Oort Cloud is so vast that its outer edge might extend as far as 100,000 astronomical units from the Sun, where 1 astronomical unit is the distance between Earth and the Sun, roughly 93 million miles. So when you do the math, you're looking at something that could stretch nearly 2 light years away, which starts to put it in the territory of being closer to the nearest star than to our own Sun. To truly understand how far away this is, consider that Voyager 1, the fastest and most distant spacecraft humanity has ever launched, has been traveling through space for over 47 years now, at a speed of about 38,000 miles per hour, and it still hasn't reached the Oort Cloud yet. In fact, scientists calculate it will take another 300 years for Voyager 1 to finally arrive at the inner edge, and then another 30,000 years to actually traverse the entire cloud and exit the other side, which means by the time that spacecraft finally leaves the Oort Cloud, humanity as we know it today will likely be completely unrecognizable, if we even still exist at all. The existence of the Oort Cloud was first theorized back in 1950 by a Dutch astronomer named Jan Oort, who noticed something peculiar about certain comets that would occasionally appear in our night sky. These weren't the regular short-period comets that orbit the sun every few years or decades. These were long-period comets that would show up seemingly out of nowhere with orbits that took hundreds, thousands, or even millions of years to complete. And what really puzzled astronomers was that these comets could come from any direction. Unlike the planets and asteroids that all orbit in roughly the same flat plane around the Sun, these long-period comets would dive in from above, below, or from the sides, coming at us from all angles, as if they were falling toward the Sun from some massive spherical shell surrounding everything. Jan Oort realized that there must be a vast reservoir of icy objects out there at the very edge of the solar system, a place where the Sun's gravity was just barely strong enough to hold on to these frozen chunks, but weak enough that any small disturbance could send them tumbling inward on a collision course with the inner solar system. And his theory has held up remarkably well over the decades. Even though we still can't directly see the Oort cloud itself, we can see the evidence of its existence every time one of these ancient comets comes blazing through our neighborhood. The structure of the Oort cloud is actually thought to consist of two distinct regions. There's the inner Oort cloud, sometimes called the Hills cloud, after astronomer Jack Hills, who proposed its existence in 1981, which is shaped more like a donut or torus, and is much denser with perhaps tens or hundreds of times more cometary material than the outer region. And then there's the outer Oort cloud, the massive spherical shell that extends for potentially a light year or more in all directions. And together, these two regions form the absolute frontier of our solar system's gravitational influence. What makes the Oort cloud so fascinating and so dangerous is how it formed in the first place. Billions of years ago, when the solar system was young and chaotic, the region around the newly formed Sun was filled with countless chunks of material called planetesimals. These were the building blocks that eventually clumped together to form the planets we know today. But not all of them made it into planets. Many of these icy and rocky chunks got caught in gravitational interactions with the giant planets, especially Jupiter and Saturn, whose enormous masses acted like cosmic slingshots, flinging debris in all directions with tremendous force. Some of this material was ejected from the solar system entirely, sent flying off into interstellar space, never to return. But a significant amount was thrown outward into extremely elongated orbits, where they would spend most of their time at incredible distances from the Sun, but remain just barely gravitationally bound to our star. And over millions of years, the gravitational influence of passing stars and the tidal forces from the Milky Way galaxy itself helped to circularize these orbits, somewhat settling them into the vast spherical shell we now call the Oort cloud. This means the Oort cloud is essentially a graveyard of our solar system's violent past, a collection of ancient debris that got kicked out of the neighborhood but not quite hard enough to escape completely. And because these objects have been sitting in the deep freeze for billions of years at temperatures just a few degrees above absolute zero, they've remained virtually unchanged, preserving the original composition and chemistry of the materials that formed our solar system. The objects in the Oort cloud are primarily made of frozen volatiles, substances that easily turn into gas when heated. Things like water ice, methane, ammonia, carbon monoxide, and various other frozen compounds, with some rocky material mixed in as well. And this is what makes them so different from asteroids, which are primarily rocky or metallic. Oort cloud objects are like cosmic dirty snowballs, and when one of them gets disturbed and begins falling toward the Sun, that's when we see it transform into what we call a comet, with the frozen material sublimating directly from ice to gas as it gets closer to the Sun's heat, creating the spectacular glowing coma and tail that have terrified and fascinated humans for thousands of years. But here's where things get really unsettling. The Oort cloud isn't a stable, peaceful place. It's constantly being disturbed by external forces, and because these objects are so far from the Sun's gravitational hold on them is incredibly weak, which means even small perturbations can have dramatic effects. Passing stars, for example, can gravitationally tug on Oort cloud objects as they cruise through the galaxy. And our Sun isn't stationary. It's orbiting around the center of the Milky Way galaxy, just like all the other stars, which means it periodically passes through different regions of the galaxy, with varying densities of stars and interstellar matter. And each time a star passes within a few light years of our solar system, which happens every few million years or so, its gravity can reach out and disturb the Oort cloud, nudging some objects into new orbits. And occasionally, those new orbits send them falling inward toward the Sun and toward us. Even the Milky Way galaxy itself exerts a tidal force on the Oort cloud. The galactic tide is caused by the difference in gravitational pull from the galaxy on the near side versus the far side of the Oort cloud. And this differential force can slowly perturb orbits over millions of years. And there's also the possibility of giant molecular clouds, vast regions of dense gas and dust in the galaxy, passing near our solar system and gravitationally stirring up the Oort cloud like a spoon, mixing a cosmic soup. This is why long-period comets appear so unpredictably. We can't forecast when a passing star or molecular cloud might disturb the Oort cloud and send a new batch of comets our way. They can come from any direction at any time, with virtually no warning. And this is fundamentally different from asteroids in the inner solar system, which we can track and predict with great accuracy, because their orbits are stable and well mapped. But Oort cloud objects are lurking out there in the darkness, dormant for millions of years, until something gives them a gravitational nudge, and they begin their long plunge toward the inner solar system. And by the time we detect them with our telescopes, they're already on their way in, sometimes giving us only months or years of advance warning, depending on their trajectory. The total mass of the Oort cloud is extremely difficult to estimate because we can't observe it directly. Early estimates suggested it might contain as much as 380 times the mass of Earth, but more recent analysis based on the number and size of comets we've actually observed has revised that number downward significantly. Current estimates suggest the Oort cloud might contain somewhere between 3 and 100 times Earth's mass in total, which might not sound like much spread out over such an enormous volume. But remember that this mass is concentrated in potentially trillions of discrete objects, any one of which could become a deadly projectile if sent our way. The largest known Oort cloud objects are estimated to be hundreds of miles across, true dwarf planets made of ice and rock, and if one of those were to be perturbed into an Earth-crossing orbit, the consequences would be beyond catastrophic. We're talking about an extinction-level event that could potentially wipe out not just humanity, but most life on Earth, similar to what happened 65 million years ago when a comet or asteroid struck the Yucatan Peninsula and ended the age of the dinosaurs. And the terrifying reality is that we likely wouldn't see it coming until it was far too late to do anything about it. The Oort cloud also raises profound questions about the boundaries of our solar system. Traditionally, we think of the solar system as ending somewhere around the orbit of Neptune, or maybe the Kuiper belt just beyond it. But the Oort cloud extends so far out that it's actually in interstellar space, beyond the heliosphere, which is the bubble of charged particles flowing out from the sun, called the solar wind. The heliosphere ends at a boundary called the heliopause, which is about 11 billion miles from the sun, and both Voyager spacecraft have crossed this boundary and are now in the interstellar medium. But they're still nowhere near the Oort cloud. In fact, they're not even 1/100th of the way there. So in a very real sense, the Oort cloud represents the true edge of the solar system, the farthest reach of the sun's gravitational influence, where our star's grip on matter finally gives way to the gravitational influence of other stars and the galaxy itself. Another fascinating aspect of the Oort cloud is that it might not be entirely made up of objects that formed around our sun. Recent research has suggested that when our solar system was very young, and the sun was still part of a cluster of sibling stars that all formed from the same molecular cloud, these stars were much closer together than they are now. And in that crowded stellar nursery, it's quite possible that objects were exchanged between different stellar systems. Gravitational interactions could have stripped away some objects from one star and transferred them to another, which means a significant fraction of the Oort cloud, perhaps even the majority of it, might actually consist of material that originally formed around other stars, was captured by our Sun during this early phase. And if that's true, then studying Oort cloud comets isn't just studying our own solar system's history, it's studying the formation and evolution of other stellar systems as well. Getting a glimpse at the diversity of planetary system formation across a whole cluster of stars, the inner Oort cloud, or Hill's cloud, is particularly interesting because it's thought to be much denser than the outer cloud and might serve as a reservoir that gradually replenishes the outer Oort cloud as objects are lost from the outer region due to gravitational perturbations. Without this inner reservoir, the outer Oort cloud should have been depleted long ago over the billions of years that our solar system has existed. But we continue to see long-period comets arriving, which suggests that there must be some mechanism continuously supplying new objects to the outer cloud. And the inner Oort cloud is the leading candidate for that mechanism, acting like a storage depot that slowly releases objects into the outer cloud over time. There's also the question of whether other stars have their own Oort clouds, and the answer is almost certainly yes. The process that formed our Oort cloud, the gravitational scattering of planetimals by giant planets during the early chaotic phase of solar system formation, is thought to be a common feature of planetary system development, which means that virtually every star with planets probably has its own cloud of icy debris at the outer edges of its gravitational influence, and some of those clouds might be much larger and more massive than ours, or much smaller, depending on the specific conditions during that star's planetary formation period. And this has implications for the search for life in the universe, because comets from Oort cloud-like structures might play a role in delivering water and organic compounds to rocky planets in the habitable zone, potentially seeding them with the ingredients necessary for life to emerge. The Oort cloud is also a reminder of just how empty space really is. Even though it contains trillions of objects, they're spread out over such an enormous volume that the average distance between any two objects is millions of miles. If you were somehow standing on one Oort cloud object, you wouldn't see any others with the naked eye. You'd just see the faint point of light that is our Sun in one direction, and the stars of the Milky Way in all the other directions, and you'd be utterly alone in the cold and dark, drifting for billions of years in a nearly perfect vacuum, with temperatures hovering just a few degrees above absolute zero. It's one of the most isolated and inhospitable environments imaginable, and yet it's technically still part of our solar system, still bound to our Sun by the invisible hand of gravity. One of the great mysteries surrounding the Oort cloud is what might be lurking out there that we haven't detected yet. Some astronomers have speculated about the possibility of larger bodies, perhaps even Earth-sized rogue planets, that were ejected from the inner solar system during the early chaotic period and ended up in the Oort cloud. And there have been various proposals over the years for the existence of an undiscovered planet, sometimes called Planet 9 or Planet X, that might be orbiting in the outer solar system or even in the inner Oort cloud. And while most of these proposals are highly speculative and lack solid evidence, the fact remains that the Oort cloud is so distant and dim that large objects could easily be hiding out there completely unknown to us, only revealing themselves by their gravitational influence on other objects, or if they happen to pass close enough to be detected by our telescopes. The Oort cloud also plays a role in the long-term evolution and stability of the solar system by storing such a massive amount of material at the outer edges. It acts as a kind of gravitational buffer, and the perturbations caused by passing stars that disturb the Oort cloud might also have subtle effects on the orbits of the outer planets over millions and billions of years. And there are theories that major disturbances to the Oort cloud, such as a very close stellar encounter, or the passage through a particularly dense region of the galaxy, might trigger what's called a comet shower, where hundreds or thousands of comets are simultaneously sent into the inner solar system over a relatively short period of time, geologically speaking. And some researchers have tried to correlate periods of increased impact cratering on Earth and the Moon with times when the solar system might have passed through or near spiral arms of the Milky Way, where stellar encounters would be more frequent. Though these correlations remain controversial and difficult to prove definitively, understanding the Oort cloud is also crucial for understanding the risk that comets pose to Earth. While asteroids get most of the attention in discussions about planetary defense because they're easier to track and there are well-known populations of near-Earth asteroids, the reality is that a large, long-period comet from the Oort cloud could be just as dangerous, if not more so. Comets move much faster than asteroids because they're falling in from the outer solar system, gaining tremendous speed as they approach the Sun, and that higher velocity means a higher energy impact. So even a somewhat smaller comet could deliver as much destructive energy as a larger but slower moving asteroid. And because comets are partly made of ice and volatile compounds, they can be structurally weaker and more prone to breaking apart, which could either make them less dangerous if they disintegrate high in the atmosphere, or more dangerous if they fragment into multiple large pieces that create a shotgun blast of impacts across a wide area. The study of Oort cloud comets has also revolutionized our understanding of the early solar system's chemistry. When comets from the Oort cloud come close enough to the Sun to become active, shedding gas and dust, astronomers can analyze that material with spectrographs and determine its chemical composition. And what they've found is that these comets contain a rich mixture of organic compounds, complex carbon-based molecules, including amino acids, which are the building blocks of proteins. And this has led to the theory that impacts from Oort cloud comets during Earth's early history might have delivered significant amounts of water and organic material to our planet, essentially providing some of the raw ingredients that eventually led to the emergence of life. So in a very real sense, life on Earth might owe its existence to the Oort cloud, and the cosmic violence that occasionally sends comets crashing into the inner solar system might have been a necessary step in our planet's journey from a barren rock to a living world. The Oort cloud will remain one of astronomy's great frontiers for the foreseeable future, unless we develop dramatically faster propulsion technology. Sending a spacecraft to actually explore the Oort cloud is beyond our current capabilities. The journey would take thousands of years, even with our fastest current spacecraft, and building something that could survive and function for that length of time, while also communicating back to Earth across such vast distances, presents enormous engineering challenges that we're nowhere near solving. So for now, and for probably many decades to come, our knowledge of the Oort cloud will remain indirect, inferred from the comets that occasionally visit us, and from theoretical models of solar system formation and evolution. But every long-period comet that passes through gives us another small piece of the puzzle, another glimpse into that mysterious frozen realm at the edge of everything we know. And perhaps someday, whether through revolutionary new propulsion systems or some other breakthrough we can't yet imagine, humanity will finally send emissaries to the Oort cloud to see with our own cameras and instruments what has remained hidden in the darkness for billions of years, waiting silently at the boundary between our solar system and the vast ocean of interstellar space beyond. In the year 2010, while astronomers were busy scanning the southern skies for something completely different, they stumbled upon something that would fundamentally challenge our understanding of comets and the frozen wasteland at the edge of our solar system. But they didn't realize what they had found at first. In fact, the discovery sat hidden in archived data for over a decade before anyone noticed it, buried among tens of thousands of images captured by the Dark Energy Survey, a massive astronomical project operating out of the Cerro Tololo Inter-American Observatory in Chile that was designed to study the mysterious force accelerating the expansion of the universe not to hunt for comets. Astronomers Pedro Bernardinelli and Gary Bernstein were developing sophisticated algorithms to identify trans-Neptunian objects in this vast dataset, objects beyond Neptune's orbit that could tell us about the outer solar system's structure and history. And when they set their computer programs loose on more than 80,000 images of the sky, they were looking for things that moved according to the laws of physics governing solar system objects, tracking their motion across multiple images taken over several years. And what they found defied all expectations. The object that would eventually be designated C2014UN271, but which everyone now knows as Comet Bernardinelli-Bernstein, was spotted at a distance that seemed almost impossible for a comet. It was sitting at 29 astronomical units from the Sun. When first imaged back in October 2014, which means it was almost as far out as Neptune itself, roughly 2.7 billion miles from the Sun. And this was the greatest distance at which any comet had ever been discovered. So far out that most comets at that distance should be completely frozen solid and inactive, just dark chunks of ice and rock drifting silently through space. But what really made headlines around the world, when the discovery was finally announced in June 2021, wasn't just how far away it was the absolutely staggering size of this cosmic beast. Based on the object's brightness and distance, astronomers initially calculated that the comet's nucleus, the solid core of ice and rock at its center, had to be somewhere between 60 and 120 miles across. And these numbers sent shockwaves through the astronomical community, because that's not just big for a comet, that's monumentally, almost impossibly huge. To put this in perspective, most comets that we've studied have nuclei that are maybe 1 mile across, perhaps a few miles at most. They're essentially cosmic snowballs the size of a small mountain or a large city. But Bernardinelli-Bernstein wasn't a snowball. It was more like a frozen dwarf planet, something so massive that it blurred the line between what we call a comet and what we call a minor planet. And initial estimates suggested it could be 50 times larger than typical comets, making it not just the largest comet nucleus ever discovered, but the largest by an absolutely enormous margin. Nothing else even came close. The only comets in recorded history that approached this size class were Comet Hale-Bopp, which gave us that spectacular show in the night sky back in 1997, with its brilliant twin tails visible, even from light-polluted cities, and Comet C2002VQ94, discovered by the Linear Project, which never came closer to the Sun than Jupiter's orbit, and so never developed the dramatic coma and tail that make comets so visually striking. But even these giants were thought to be maybe 20 to 30 miles across, nowhere near the 100-mile diameter being calculated for Bernardinelli-Bernstein. As astronomers around the world turned their telescopes toward this newly announced object and started digging through decades of archived observations from various sky surveys to see if they could find earlier images of it that had been missed, the story became even more fascinating and complex, because what they discovered was that Bernardinelli-Bernstein wasn't just a dead frozen rock coasting through space. It was already active, already showing signs of a coma, that hazy envelope of gas and dust that forms when a comet's ice begins to sublimate and turn directly from solid to gas without passing through a liquid phase. And this was deeply unexpected, because comets shouldn't be active at such enormous distances from the Sun. The traditional model of comet activity says that as a comet falls inward toward the Sun on its elliptical orbit, it remains frozen and inert until it gets close enough for the Sun's heat to start warming it up. And for most comets, that threshold happens somewhere around Jupiter's orbit, about 5 astronomical units from the Sun, where temperatures climb high enough for water ice to begin sublimating, creating the dramatic jets of gas and the dusty coma that make comets so spectacular to observe. But Bernardinelli-Bernstein was showing activity at 29 astronomical units, almost 6 times farther out where temperatures hover around -348 degrees Fahrenheit. Tony Farnham, a research scientist at the University of Maryland's Department of Astronomy, became fascinated by this puzzle and decided to look for Bernardinelli Bernstein in data from the Transient Exoplanet Survey Satellite, or TESS, which wasn't designed to study comets at all, but rather to search for planets around distant stars by watching for the tiny dips in brightness that occur when a planet passes in front of its host star. But TESS had one advantage for studying faint objects. It stared at the same patch of sky for 28 days at a time, taking images continuously. And Farnham realized that if he could stack thousands of these TESS images together, carefully aligning them so that the comet was in exactly the same position in each frame, he could dramatically increase the signal and see details that were invisible in any single image. When he and his colleagues performed this painstaking analysis, combining thousands of images of the comet captured between 2018 and 2020, what they saw confirmed that Bernardinelli Bernstein had indeed been active for years, surrounded by a faint but definite coma of dust and gas, which meant this monster comet had been awake and venting material into space long before anyone realized it existed. And this discovery was published in the Planetary Science Journal in November 2021, fundamentally changing our understanding of what this object was and what it could tell us about comet physics. The presence of activity at such a great distance told astronomers something crucial about what Bernardinelli Bernstein is made of, because if water ice was responsible for the coma, the comet would need to be much closer to the sun before it got warm enough for that ice to sublimate, which meant something else had to be driving the activity, some other frozen compound with a much lower sublimation temperature, something that could turn to gas even in the frigid temperatures of the outer solar system. And the leading candidates were carbon monoxide, carbon dioxide, or various other volatile ices that freeze at much lower temperatures than water. This is where the Atacama Large Millimeter Submillimeter Array, or ALMA, came into the picture. ALMA is one of the most powerful radio telescope facilities on Earth, located high in the Chilean Andes, at an altitude of over 16,000 feet, where the thin, dry air allows for incredibly sensitive observations of faint radio emissions from space. And ALMA specializes in detecting the signatures of specific molecules by observing the radio frequencies they emit. Each molecule has a unique spectral fingerprint, and ALMA's sensitivity is so extraordinary that it can detect these molecular emissions from objects billions of miles away. When astronomers trained ALMA on Bernardinelli Bernstein, they made a discovery that was truly groundbreaking. They detected clear, unambiguous signatures of carbon monoxide gas erupting from the comet, explosive jets of CO molecules being vented into space. And this was the very first time that molecular outgassing had ever been directly detected and measured in a comet at such an extreme distance from the sun, providing direct chemical evidence of what was powering the comet's activity. The significance of this discovery cannot be overstated. Carbon monoxide ice has a sublimation temperature that's much lower than water ice. It can turn directly from solid to gas at temperatures as low as -370 degrees Fahrenheit, which means it can drive comet activity at distances where water ice would remain completely frozen. And by detecting these CO emissions, scientists weren't just solving the puzzle of why Bernardinelli Bernstein was active so far from the sun. They were getting direct chemical analysis of primordial materials that have been preserved unchanged in the deep freeze of the Oort Cloud for 4.6 billion years, since the very formation of our solar system. This is like finding a perfectly preserved time capsule from the birth of the planets, because objects in the Oort Cloud were ejected from the inner solar system during the chaotic early period when the giant planets were still migrating and their gravity was flinging debris in all directions. And once these objects reached the cold darkness beyond the planets, they froze solid and have remained essentially unchanged ever since. So every molecule of carbon monoxide, every grain of dust, every bit of rock and ice in Bernardinelli Bernstein is a sample of the original materials that existed in the solar nebula, the disk of gas and dust that surrounded the young sun and from which all the planets eventually formed. The detection of carbon monoxide also challenged traditional models of how comets work. Most of our understanding of comet behavior comes from studying comets that enter the inner solar system, where water-ice sublimation dominates the activity, creating the spectacular tails and jets we associate with comets. But Bernardinelli Bernstein was demonstrating that at extreme distances, completely different physics takes over, with exotic volatile ices like carbon monoxide driving the show. And this suggested that the largest objects in the Oort Cloud might behave like a completely different class of comet, powered by different chemistry and following different rules than the smaller comets we're used to studying. As observations accumulated and analysis became more refined, astronomers were able to nail down the size of Bernardinelli Bernstein's nucleus more precisely, and NASA's Hubble Space Telescope played a crucial role in this measurement, using its exquisite resolution to separate the light coming from the solid nucleus from the light scattered by the surrounding coma of dust and gas, which is a tricky business because the coma makes the comet appear brighter and larger than it actually is. And if you don't account for that contamination, you'll overestimate the nucleus size. The Hubble observations, published in April 2022, confirmed that while Bernardinelli Bernstein was indeed enormous, it wasn't quite as gigantic as the most optimistic initial estimates had suggested. The nucleus was measured at approximately 85 miles across, or about 137 kilometers in diameter, which is still absolutely massive, still by far the largest comet nucleus ever confirmed, still 50 times larger than typical comets, but somewhat smaller than the 120-mile upper limit that had been suggested when the comet was first discovered. And the reason for the revision was precisely because the comet had turned out to be active, with the coma's light adding to the nucleus's brightness and fooling earlier size estimates. Even at 85 miles across, Bernardinelli Bernstein is a true monster. To give you a sense of scale, this is larger than the distance between Boston and New York City. If this comet were sitting on Earth's surface, it would stretch across multiple states, and its mass is estimated at around 500 trillion tons, which is roughly 500 million times the mass of a typical comet. This is so massive that it's classified as a minor planet as well as a comet, occupying that fuzzy boundary zone between the two categories. The orbit of Bernardinelli Bernstein is equally mind-blowing. Astronomers calculated that it follows an extremely elongated elliptical path that takes approximately 3 million years to complete one full orbit around the Sun, which means the last time this comet was in the inner solar system, our human ancestors didn't exist yet. The planet was in the middle of an ice age, and the creatures walking around were very different from anything alive today. And when it completes its current journey and heads back out to the cold darkness, it won't return until 3 million years in the future, a time span so vast that it's impossible to imagine what Earth and humanity might look like then, assuming we still exist at all. At its farthest point, Bernardinelli Bernstein travels approximately half a light year from the Sun, which puts it well into the Oort Cloud, in that mysterious spherical shell of icy debris that represents the absolute frontier of our solar system's gravitational influence. And at that distance, the Sun appears as nothing more than a bright star among all the other stars in the sky, providing essentially zero heat or light. And the comet drifts through that darkness for millions of years, frozen solid at temperatures just barely above absolute zero, until the gentle tug of gravitational perturbations from passing stars or the tidal force of the galaxy itself nudges it into a new orbit, and it begins falling back toward the inner solar system. Right now, as of 2025, Bernardinelli Bernstein is inbound, falling toward the Sun at a speed of approximately 22,000 miles per hour, and it's currently less than 2 billion miles from the Sun. which sounds like a lot, but is actually relatively close by astronomical standards, about the distance to Uranus. And as it continues its inward journey, it will get warmer and more active. The carbon monoxide jets will intensify, and eventually, it will become active enough to develop a visible tail, though it will never come close enough to be visible to the naked eye from Earth, which is probably a good thing, because if something this massive ever did become a bright naked eye comet, it would be both spectacular and terrifying. The comet will reach its closest approach to the Sun in January 2031, when it will arrive at a distance of 10.9 astronomical units, which will place it just outside Saturn's orbit, still far from Earth and the inner planets. And then it will swing back around and begin its long 3 million-year journey back out to the Oort Cloud, gradually fading from view as it moves away and cools down, eventually returning to its frozen dormant state until something disturbs it again. Millions of years from now, the discovery of Bernardinelli, Bernstein, has profound implications for our understanding of the Oort Cloud and how many large objects might be lurking out there undetected. If there's one comet this large, there could be others, perhaps many others, and while most of them would be in orbits that keep them far from Earth, there's always the possibility that gravitational perturbations could send one on a trajectory toward the inner solar system. And unlike asteroids, which come from the relatively nearby asteroid belt and move at speeds we can track and predict, a large Oort Cloud comet would be approaching from the darkness beyond the planets, moving at tremendous velocity, and we might have very little warning before it arrived. The molecular activity detected in Bernardinelli Bernstein also opens up new avenues for understanding the chemistry of the early solar system. By observing how the carbon monoxide sublimates and what other molecules might be present in the coma, astronomers can piece together the conditions that existed in the outer solar nebula 4.6 billion years ago, determining what volatiles were available, what temperatures different regions of the disk experienced, and how materials were distributed during the planet formation process. And this information helps constrain models of how planetary systems form, not just in our solar system, but around other stars throughout the galaxy. One of the most intriguing questions about Bernardinelli Bernstein is whether it will fragment or break apart as it continues its approach to the Sun. Large comets are notoriously fragile because they're not solid rock, but rather loose agglomerations of ice and dust held together by their own weak gravity. And as they heat up and volatile ices sublimate, the outgassing can create stresses that crack and fracture the nucleus, sometimes breaking it into multiple pieces, and we've seen this happen with several comets in the past. Most famously Comet Shoemaker-Levy 9, which broke into more than 20 fragments before crashing into Jupiter in 1994, creating a spectacular series of impacts that were visible from Earth. If Bernardinelli Bernstein were to fragment, it would be an unprecedented opportunity to study the interior composition of the largest comet ever found, because the fresh surfaces exposed by the breakup would reveal materials that have been hidden beneath the surface crust, potentially including ices and organic compounds that have never been exposed to sunlight or space weathering. Though given the comet's enormous size and mass, it's probably stable enough to survive its perihelion passage intact. But astronomers will be watching closely for any signs of cracking or splitting as it continues to approach the Sun over the next several years. The fact that Bernardinelli Bernstein is so large also raises questions about how it formed in the first place. Most comets are thought to be the leftover building blocks that never quite made it into planets, fragments of the protoplanetary disk that got scattered outward before they could accumulate into anything larger. But something the size of Bernardinelli Bernstein is approaching the scale of dwarf planets like Pluto or Eris, which suggests it might have undergone at least some degree of gravitational collapse and internal differentiation, where heavier materials sink toward the center and lighter materials rise to the surface, creating a layered structure rather than a uniform mixture of ice and rock throughout. As observations continue, and more data is collected. Bernardinelli Bernstein is helping astronomers refine their estimates of how many large objects exist in the Oort Cloud and what the total mass of that distant reservoir might be. Current estimates suggest the Oort Cloud could contain anywhere from 3 to 100 Earth masses worth of material, spread across trillions of objects. But there's huge uncertainty in these numbers, precisely because we can't directly observe most of what's out there. And every new large comet that's discovered provides another data point, helping to constrain these estimates. And Bernardinelli Bernstein, as the largest ever found, is an especially valuable data point, suggesting that the upper end of the size distribution extends to at least 85 miles and possibly larger. The discovery also demonstrates how much is still waiting to be found hidden in archival data. Bernardinelli Bernstein was sitting right there in the dark energy survey images for years before anyone noticed it. And there are undoubtedly other significant discoveries waiting to be made by people clever enough to develop the right algorithms and willing to put in the computational effort to analyze millions of images, looking for patterns and movements that reveal previously unknown objects. And as new sky surveys come online, with even more powerful cameras and telescopes covering larger areas of the sky with better sensitivity, we can expect to find more monsters like Bernardinelli Bernstein, and perhaps even larger ones that are currently beyond the detection limits of our telescopes. What makes Bernardinelli Bernstein truly special, though, isn't just its size, but the fact that we're able to study it in such detail while it's still far from the sun. Most comets don't become easy targets for detailed observation until they're well into the inner solar system, where they're bright and active and developing spectacular tails. But by that point, they've been heavily modified by solar heating and radiation, with their surface layers stripped away and their composition altered, whereas Bernardinelli Bernstein is giving us a chance to observe a pristine Oort Cloud object while it's just beginning to wake up, when it's still relatively close to its frozen dormant state. And this provides an unprecedented window into the true primordial composition of these ancient time capsules from the birth of our solar system. And that opportunity, that chance to directly sample materials that have been preserved unchanged for billions of years, is what makes this monster comet not just a curiosity, but a profound scientific treasure that will continue yielding discoveries for years to come as it approaches its closest point to the sun and then recedes back into the darkness from which it came. The detection of carbon monoxide gas erupting from Comet Bernardinelli Bernstein represents one of the most significant breakthroughs in cometary science in decades, because for the first time in human history, astronomers were able to directly measure and analyze the molecular outgassing of a comet at an unprecedented distance from the sun, providing a chemical fingerprint of materials that have been frozen and preserved in pristine condition since the solar system formed 4.6 billion years ago. And what makes this discovery so extraordinary isn't just that they detected these molecules, but what those molecules tell us about the ancient chemistry of our solar system's birth and the building blocks that eventually came together to form the planets we know today. When the Atacama Large Millimeter Submillimeter Array pointed its 66 radio antennas toward this distant comet and began collecting data, the astronomers weren't entirely sure what they would find. They knew the comet was active, based on optical observations showing a faint coma, but identifying exactly which molecules were driving that activity required the incredible sensitivity and spectral resolution that only ALMA can provide. And what they detected was an unambiguous signature at a frequency of 230 gigahertz, which corresponds exactly to the rotational transition of carbon monoxide molecules, specifically the transition labeled J equals 2 to 1 in spectroscopic notation, which is like a fingerprint that only carbon monoxide can produce. Carbon monoxide is a simple molecule consisting of one carbon atom bonded to one oxygen atom. And while it's deadly poison to humans because it binds to hemoglobin in our blood and prevents oxygen transport, in the context of cometary science, it's absolutely fascinating because CO has some unique properties that make it behave very differently from the water ice that dominates most. Comet activity. The key difference is the sublimation temperature, which is the temperature at which a substance transitions directly from solid to gas without passing through a liquid phase. And for carbon monoxide ice, this happens at around -370 degrees Fahrenheit or -223 degrees Celsius, which is much, much colder than the temperature required for water ice to sublimate. Water ice needs to reach around -140 degrees Fahrenheit or -96 degrees Celsius before it starts turning to vapor at a significant rate, which is why most comets don't become active until they're inside Jupiter's orbit at around 5 astronomical units from the Sun, where solar heating can warm them enough. But Bernardinelli Bernstein was showing activity at distances greater than 20 astronomical units, which meant temperatures were far too cold for water ice sublimation. And the only way to explain the observed coma was if something with a much lower sublimation temperature was driving the outgassing. And carbon monoxide was the perfect candidate, along with possibly carbon dioxide, which also sublimates at very low temperatures. And when ALMA detected those co-emissions, it confirmed what scientists had suspected, but could never directly prove before, that these ultra-distant comets are powered by exotic volatile ices that can turn to gas even in the frigid temperatures of the outer solar system, where water remains frozen as hard as granite. The ALMA observations didn't just detect carbon monoxide, they measured how much was being produced, calculating what's called the production rate, which tells you how many molecules per second are being vented into space. And for Bernardinelli Bernstein, they measured a CO production rate on the order of 10 to the power of 28 molecules per second, which is an absolutely staggering number. Billions of trillions of carbon monoxide molecules erupting from the comet's surface every single second, creating jets and streams of gas that flow outward from the nucleus and spread into the surrounding space. And by measuring the strength of these emissions at different times and from different regions of the comet, astronomers could map out where the active areas were located and how the outgassing varied across the surface. What made the ALMA observations even more valuable was that they could measure not just the presence of carbon monoxide, but also its velocity. Because when molecules are moving toward or away from us, the frequency of the light they emit gets shifted by the Doppler effect, the same phenomenon that makes an ambulance siren sound higher pitched when it's approaching and lower pitched when it's receding. And by carefully measuring these frequency shifts in the CO emission, astronomers could determine that the gas was flowing outward from the nucleus at speeds of several hundred meters per second, and they could even see evidence of jets, concentrated streams of gas erupting from specific active regions on the comet's surface, rather than a uniform sublimation from the entire surface, which tells us that the nucleus has areas that are more volatile rich or more directly illuminated by the sun, creating localized hotspots that drive most of the activity. The chemical composition revealed by these observations provides a direct window into the conditions that existed in the outer regions of the solar nebula 4.6 billion years ago, when the sun was just forming and the planets were beginning to coalesce from the disk of gas and dust that surrounded it, because the materials in Bernardinelli Bernstein were formed in that environment, condensing out of the nebular gas when temperatures dropped low enough for various compounds to freeze. And different substances freeze at different temperatures. So by looking at what's present in the comet and in what proportions, scientists can reconstruct the temperature and pressure conditions that must have existed in that region of the disk when these materials formed. Carbon monoxide is particularly interesting from a chemical evolution perspective because it's one of the fundamental building blocks of organic chemistry, the branch of chemistry dealing with carbon-based compounds. And while CO itself is not an organic molecule in the strict sense, because it doesn't contain any hydrogen, it can serve as a starting point for more complex chemistry. In the presence of ultraviolet light or cosmic rays, or other energy sources. Carbon monoxide can react with hydrogen to form formaldehyde, which is written as H2CO, and formaldehyde can then undergo further reactions to produce methanol, written as CH3OH, and methanol can polymerize to form larger organic molecules, and this chain of reactions can eventually lead to the amino acids and other prebiotic compounds that are thought to be essential precursors to life. So detecting carbon monoxide in pristine cometary material tells us that the raw ingredients for this kind of chemistry were present in the early solar system, locked away in icy bodies, and occasionally delivered to the inner solar system through comet impacts. The ALMA team also searched for other molecules in Bernardinelli Bernstein's coma, looking for emission lines corresponding to formaldehyde, methanol, hydrogen cyanide, written as HCN, and various other compounds that have been detected in other comets. And while they didn't find clear detections of most of these molecules, that doesn't necessarily mean they're not there. It could simply mean that they're present in much smaller quantities than carbon monoxide, below ALMA's detection threshold at the distances and integration times used for these observations. And as the comet continues approaching the Sun and becomes more active, other volatile species will likely start sublimating in detectable quantities, giving astronomers the chance to build up a complete inventory of what's frozen inside this ancient time capsule. One of the most profound implications of detecting carbon monoxide at such great distances is what it tells us about the formation location of Oort Cloud objects. There's been a long-standing debate in planetary science about where these distant comets originally formed before being scattered outward by gravitational interactions with the giant planets. Some models suggest they formed in the outer regions of the solar system, beyond Neptune, where temperatures were cold enough for highly volatile ices, like carbon monoxide, to condense, while other models propose they formed closer in, perhaps in the region where Jupiter and Saturn are now, and were then flung outward. And the chemical composition of Oort Cloud comets can help settle this debate, because different formation locations would have different temperatures and different available materials, leading to different chemical signatures in the resulting comets. The high abundance of carbon monoxide in Bernardinelli Bernstein suggests it formed in a very cold environment where CO could freeze out along with water and other ices. And this points toward a formation location in the outer solar system, probably somewhere in the region where Neptune and the Kuiper Belt are now, where temperatures in the solar nebula would have been low enough for carbon monoxide ice to be stable. And this is consistent with models showing that the giant planets, especially Neptune and Uranus, scattered large numbers of planetesimals outward into the Oort cloud during their migration through the early solar system. So Bernardinelli Bernstein is likely a refugee from the Neptune zone, a chunk of primordial ice and rock that got kicked out to the edge of the solar system billions of years ago and has been drifting in cold storage ever since. The detection of molecular outgassing also allows scientists to study the physical processes happening on and just below the comet's surface. When sunlight hits the nucleus, even at great distances where the intensity is very weak, it still deposits some energy into the surface layers, and this energy can penetrate a few centimeters or even meters into the porous icy material, warming up subsurface layers and causing volatile ices to sublimate. And the gas produced by this sublimation has to escape somehow, either by diffusing up through the porous surface material or by breaking through in explosive bursts when pressure builds up beneath a less permeable crust, and by observing how the outgassing varies with time and with the comet's rotation. Astronomers can constrain models of heat transport and gas diffusion in cometary nuclei, which helps us understand not just Bernardinelli Bernstein, but comets in general and how they evolve as they approach the Sun. Another fascinating aspect of the carbon monoxide detection is what it reveals about the comet's internal structure and how well mixed its composition is. If the CO was only present in a thin surface layer, it would have been depleted long ago during previous passages through the inner solar system. but the fact that it's still actively outgassing suggests either that this is Bernardinelli-Bernstein's first visit to the inner solar system in millions of years, so its volatile reserves are still intact, or that the carbon monoxide is distributed throughout the nucleus at depth, so even as surface layers sublimate away, fresh material from below is continuously exposed. And given the comet's enormous size and the fact that it never comes closer to the Sun than Saturn's orbit, it's likely that it has vast reserves of volatile ices that will continue driving activity for thousands or millions of years into the future, making it a renewable source of information about primordial solar system chemistry. The temperature at which carbon monoxide sublimation becomes significant is also important for understanding the thermal environment at the edge of the solar system. At 16 to 20 astronomical units from the Sun, where Bernardinelli-Bernstein was when the ALMA observations were made, the solar flux is incredibly weak, only about 2.5%, as intense as what we receive here on Earth. And you might think that wouldn't be enough to heat anything up. But cometary surfaces are not like planetary surfaces. They're covered with dark dust and organic material that absorbs sunlight very efficiently, and even tiny amounts of absorbed energy can raise the temperature of the surface layers above the ambient temperature of space. And for a surface coated with dark material, at 16 astronomical units, temperatures can climb to around -300 degrees Fahrenheit or so, which is just barely warm enough to start sublimating carbon monoxide ice at a detectable rate. And this explains why the comet became active at precisely the distance where it was discovered. It had reached the threshold where solar heating became sufficient to drive CO sublimation. The study of ancient chemistry, preserved in comets, also connects to the broader question of how organic molecules and the building blocks of life are distributed throughout the universe. Because if comets in our solar system contain carbon monoxide and other organic precursors, and if the processes that formed our solar system are common around other stars, then comets around those stars should also contain similar materials, and some of those comets might impact planets in the habitable zones of their systems, delivering water and organic compounds, just as they did in our early solar system. And this could be a universal mechanism for seeding planets with the ingredients necessary for life to emerge, making comets not just interesting scientific curiosities, but potentially crucial players in the origin of life on Earth and possibly elsewhere in the galaxy. The ALMA observations also demonstrated the power of radio astronomy for studying faint, distant objects that are difficult or impossible to observe with optical telescopes. Because while optical telescopes see reflected sunlight, radio telescopes can detect the actual molecular emissions from the coma, which provides direct chemical information rather than just brightness measurements. And this is especially valuable for distant comets that are too faint to show up clearly in optical images, or that have Comet too diffuse to analyze with traditional spectroscopy. And as radio telescope facilities continue to improve in sensitivity and resolution, we can expect more discoveries of molecular outgassing in distant comets, building up a comprehensive picture of what the Oort Cloud population is made of and how it compares to other comet reservoirs like the Kuiper Belt. One of the surprising findings from the ALMA data was the detection of jets and asymmetric outgassing patterns. Rather than a uniform spherical coma, the carbon monoxide emissions showed distinct directionality, suggesting that specific regions of the nucleus were more active than others, and this could be due to compositional variations across the surface, with some areas richer in volatile ices than others, or it could be due to the comet's rotation, which would cause different parts of the surface to be illuminated by the sun at different times, heating up and becoming active in a cyclical pattern. And by monitoring how these jets change over time, as the comet rotates and as it moves closer to the sun, astronomers can map out the distribution of volatile materials across the nucleus and understand how the comet's shape and spin state influence its activity patterns. The carbon monoxide production rate, measured by ALMA, can also be used to estimate how much mass the comet is losing through outgassing, because every molecule of CO that escapes carries away a tiny amount of mass. And when you multiply the number of molecules per second by the mass of each molecule, you get the mass loss rate. And for Bernardinelli Bernstein, this works out to several kilograms per second, or perhaps tens of kilograms per second, depending on exactly how the calculation is done, which might not sound like much for an object weighing 500 trillion tons. But over the course of years and decades, as the comet approaches the sun and activity intensifies, this can add up to millions or billions of tons of material lost, gradually shrinking the nucleus and changing its surface characteristics. And by comparing mass loss rates, measured at different distances from the sun, scientists can build models of how the comet will evolve during its current passage and predict what it will look like when it reaches perihelion in 2031. The chemistry revealed by carbon monoxide detection also has implications for understanding the isotopic composition of the early solar system, because molecules, like CO, can come in different isotopic forms, depending on whether the carbon atom is carbon-12 or carbon-13, and whether the oxygen is oxygen, 16, 17, or 18. And the ratios between these different isotopes can tell us about the temperature and chemical conditions under which the molecules formed. And while the initial ALMA observations of Bernardinelli Bernstein weren't sensitive enough to measure isotopic ratios, future observations with longer integration times or with the comet at a closer distance might be able to detect these subtle differences, providing even more detailed information about the comet's formation environment and how it compares to other solar system objects and to interstellar material observed in molecular clouds. Another intriguing question raised by the carbon monoxide detection is whether other ultra-volatile species might also be present. Substances like methane, written as CH4, nitrogen written as N2, or argon, all of which have even lower sublimation temperatures than carbon monoxide and could potentially be outgassing from Bernardinelli Bernstein if the nucleus is cold enough in its interior. Though detecting these species would be extremely challenging because they don't have strong spectral lines in the radio wavelengths that ALMA observes. But as the comet continues its approach and more instruments observe it across different wavelengths, we might get lucky and detect emissions from these exotic ices, which would provide an unprecedented look at the most volatile and most pristine materials from the solar system's formation. The long-term monitoring of Bernardinelli Bernstein's chemical evolution as it approaches the sun will also test our understanding of how cometary activity changes with distance. There's a concept in cometary science called the snow line or frost line, which is the distance from the sun at which a particular volatile species transitions from being frozen to being gaseous, and different molecules have different snow lines. Carbon monoxide snow line is much farther out than water's snow line, which is much farther out than the snow lines for more refractory materials like rock and metal. And as Bernardinelli Bernstein crosses these various snow lines during its inbound journey, different types of activity should turn on first carbon monoxide, which is already active, then possibly carbon dioxide and other intermediate volatiles, and eventually water ice when it gets close enough. And by watching this progression, astronomers can directly observe the stratification of volatiles in a cometary nucleus and understand how comets change their behavior depending on their distance from the sun. The detection of carbon monoxide in Bernardinelli Bernstein also validates theoretical predictions made decades ago about what should be present in Oort Cloud comets. Astronomers have long suspected that these distant objects should be rich in super volatile ices because they formed in the cold outer regions of the solar nebula and have never been heated enough to lose these materials. Unlike Jupiter family comets, which orbit closer to the sun and have been thermally processed over many orbits, losing their most volatile components and leaving behind a crust of less volatile material. So finding abundant carbon monoxide in an Oort Cloud comet confirms that these objects really are as pristine and chemically rich as theory predicted, and this gives us confidence that other Oort Cloud comets will show similar compositions when we get the chance to observe them in detail. The ancient chemistry, preserved in Bernardinelli, Bernstein, also provides a comparison point for understanding comets observed around other stars. In recent years, astronomers have detected cometary activity in debris disks around young stars, and have even observed exocomets transiting in front of their host stars, causing small dips in brightness as their dusty tails pass across the stellar disk. And while we can't yet measure the detailed chemical composition of these exocomets, we can make predictions based on what we know about comets in our own solar system. And if Bernardinelli Bernstein is representative of large Oort Cloud comets, then we might expect similar objects in other planetary systems to also contain abundant carbon monoxide and other volatile ices, and this could have implications for the delivery of organic materials and water to exoplanets, potentially influencing their habitability and the likelihood of life emerging. As scientists continue to analyze the ALMA data and combine it with observations from other telescopes across different wavelengths, they're piecing together an increasingly detailed picture of what Bernardinelli Bernstein is made of and what that tells us about the early solar system. Every new detection adds another piece to the puzzle. Every non-detection provides an upper limit that constrains the possible compositions, and together these observations are transforming this comet from a mere curiosity into a Rosetta Stone for understanding the chemistry and physics of solar system formation. And the fact that we're able to study it in such detail, while it's still relatively pristine and far from the sun, makes it an irreplaceable scientific resource that will continue yielding discoveries for years to come as more data is collected and analyzed. When people first heard about Comet Bernardinelli Bernstein, a frozen monster 85 miles across, hurtling through space from the ancient graveyard at the edge of our solar system, the immediate question on everyone's mind was terrifyingly simple. Could it hit us? And if it did, what would happen to life on Earth? And this is not an irrational fear, because 65 million years ago, something similar came screaming out of the darkness and slammed into what is now the Yucatan Peninsula in Mexico, creating an impact so catastrophic that it ended the age of the dinosaurs and wiped out 75% of all species on the planet, in an event we now call the Cretaceous Paleogene extinction. And the object that caused that apocalypse was probably somewhere between 6 and 9 miles across, which means Bernardinelli Bernstein is roughly 10 times larger, carrying potentially 1,000 times more mass and kinetic energy. So if something that size ever hit Earth, it wouldn't just be an extinction event, it would be a planet-altering catastrophe that could potentially sterilize the entire surface, boiling away the oceans, and turning the atmosphere into a hellscape of superheated rock vapor that would take millions of years to cool down and settle. The good news, the thing that lets astronomers and planetary defense specialists sleep at night, is that Bernardinelli Bernstein poses absolutely no threat to Earth. Not now, not during its upcoming closest approach in January 2031, and not for millions of years into the future, because the comet's orbit is extremely well established after more than a decade of observations, and those observations show with absolute certainty that it will reach its perihelion, its closest point to the Sun, at a distance of about 10.97 astronomical units, which puts it just outside Saturn's orbit at roughly 1 billion miles from the Sun, and Earth orbits at 1 astronomical unit. So at its closest, this comet will still be nearly 11 times farther from the Sun than we are, and there is no chance whatsoever that it will swing inward toward the inner solar system, where Earth and the other rocky planets orbit. But while Bernardinelli Bernstein itself isn't a threat, the mere fact that it exists, and that it came from the Oort Cloud, raises some deeply unsettling questions about what else might be lurking out there in that frozen wasteland, and whether future visitors from that region might not be so harmlessly aligned. Because if there's one comet 85 miles across, there are probably others, perhaps dozens or hundreds of similar giants, drifting in the darkness. And while most of them will remain in stable orbits for millions or billions of years, there's always the possibility that something could disturb them, a passing star, a close encounter with another massive Oort Cloud object, or even the gravitational tides from the Milky Way galaxy itself. And when that happens, when one of these frozen mountains gets nudged into a new trajectory, it could begin falling toward the inner solar system, and depending on the exact angle and velocity of that perturbation, it might end up on a collision course with Earth. And unlike asteroids from the asteroid belt between Mars and Jupiter, which move relatively slowly and can be tracked for years or decades before they pose any danger, comets from the Oort Cloud come in fast, really fast, because they're falling from such enormous distances that they build up tremendous velocity as the sun's gravity accelerates them inward. And by the time they reach Earth's orbit, long-period comets can be traveling at speeds of up to 100,000 miles per hour or more, compared to typical asteroid impact speeds of around 45,000 miles per hour. And that higher velocity translates directly into higher impact energy, which is why even a somewhat smaller comet can be just as destructive as a larger but slower moving asteroid. The fundamental problem with Oort Cloud comets as potential threats is the warning time, or rather the lack thereof. When astronomers discover a new asteroid in the inner solar system, they can calculate its orbit with high precision and predict where it will be years or even decades into the future, giving planetary defense teams plenty of time to plan a response if the object turns out to be on a collision course with Earth. But comets from the Oort Cloud don't give us that luxury. They can appear seemingly out of nowhere with very little advance notice, and by the time we detect them and realize they're dangerous, it might be too late to do anything about it, except evacuate whoever we can and prepare for the catastrophic consequences. Consider this scenario. A comet roughly the size of Bernardinelli Bernstein, let's say 50 miles across, gets disturbed by a passing star 20 million years ago and begins falling toward the inner solar system. It spends millions of years coasting through the darkness, gradually picking up speed as it gets closer to the sun, and then one night, an astronomer conducting a routine sky survey notices a faint smudge of light that wasn't there the previous week. Follow-up observations confirm it's a comet with a well-developed coma, and orbital calculations reveal the trajectory. And those calculations show, with sinking certainty, that this object is going to pass very close to Earth's orbit, close enough that there's a real possibility of a collision. And when they work out the timing, they realize the comet will reach Earth's orbital distance in just 18 months, which is nowhere near enough time to mount any kind of meaningful defense with our current technology. We have no spacecraft capable of intercepting and deflecting something that massive moving that fast. And even if we did, the logistics of launching such a mission, targeting the comet, and successfully altering its trajectory would be enormously challenging, and probably impossible, with only a year and a half of lead time. So we'd be left with nothing to do but watch it approach and hope that the orbital uncertainties work in our favor and it misses us. The impact of a 50-mile wide comet hitting Earth at typical long-period comet velocities would be beyond anything in human experience or imagination. The kinetic energy released would be measured in billions of megatons of TNT equivalent, millions of times more powerful than all the nuclear weapons ever built combined. The initial impact would vaporize the comet and excavate a crater hundreds of miles across, hurling millions of cubic miles of rock and debris into the atmosphere and into space. The shock wave would flatten everything within 1,000 miles of ground zero, triggering earthquakes more powerful than anything in the geological record, and generating tsunamis thousands of feet high that would inundate coastlines around the entire planet. The heat pulse from the impact would ignite global wildfires, burning forests and grasslands on every continent, and the debris lofted into the atmosphere would block out the sun for years or possibly decades, causing temperatures to plummet and photosynthesis to cease. collapsing the food chain from the bottom up, and any survivors of the initial impact and its immediate consequences would face a world of permanent twilight, freezing temperatures, poisoned water supplies, and no agriculture. And it's difficult to imagine human civilization surviving such an event, let alone most of the complex life on the planet. Now, before this all sounds too much like a disaster movie, it's important to put the actual risk in perspective. Impacts from Oort Cloud comets are extremely rare on human timescales. The best estimates suggest that Earth experiences a major impact from a comet or asteroid large enough to cause global devastation roughly once every 50 million to 100 million years, which means any individual human or even any individual generation has an extremely low probability of experiencing such an event. And most impacts come from asteroids in the inner solar system rather than comets from the Oort Cloud, simply because there are more asteroids in Earth-crossing orbits. But that doesn't mean the comet threat is zero. It just means it's a low probability, high consequence scenario that we need to take seriously, even if the odds of it happening in our lifetimes are vanishingly small. One of the challenges in assessing the comet threat is that we don't have a complete census of what's in the Oort Cloud, unlike near-Earth asteroids, which we've been systematically cataloging for decades. The objects in the Oort Cloud are too distant and too faint to detect until they start falling inward and brightening as they approach the sun, so we have to make estimates based on the number of long-period comets we observe each year and work backwards to calculate how many objects must be in the source reservoir to produce that observed rate. And those estimates suggest there are trillions of objects in the Oort Cloud, but most of them are small, kilometer-sized, or smaller, and only a tiny fraction are large enough to pose a global threat. But even if large comets represent just 1 in a million of all Oort Cloud objects, that still leaves potentially millions of them out there, any one of which could be perturbed onto an Earth-threatening trajectory at any time. Jupiter plays a fascinating and complex role in protecting Earth from comet impacts. The giant planet's enormous mass and gravitational influence act like a cosmic vacuum cleaner, either capturing or deflecting many objects that venture into the inner solar system. And studies have shown that without Jupiter, Earth would experience significantly more impacts from asteroids and comets, perhaps 5 to 10 times as many, which might have made the evolution of complex life much more difficult or even impossible, because frequent catastrophic impacts would repeatedly reset the evolutionary clock. But Jupiter is not a perfect shield. Sometimes its gravity can actually work against us. The same gravitational interactions that deflect some objects can also perturb others into Earth-crossing orbits, and there's strong evidence that Jupiter's gravity was responsible for redirecting the object that ultimately caused the dinosaur extinction, whatever initially knocked that comet or asteroid onto a trajectory toward the inner solar system. Whether it was a collision in the asteroid belt or a perturbation from another planet, it was probably Jupiter's gravitational influence during a close passage that gave it the final nudge that sent it on a collision course with Earth. The detection and tracking capabilities we've developed for near-Earth asteroids could in theory be applied to long-period comets as well. And there are several major sky surveys currently operating that scan large swaths of the sky every night looking for moving objects. These surveys can detect comets when they're still quite distant, potentially giving us years of warning rather than months, though the exact amount of warning depends on how bright the comet is and how large its coma becomes. A very active comet with a prominent tail might be detected while still beyond Jupiter's orbit, giving us 5 to 10 years of advance notice, whereas a less active comet that doesn't develop much of a coma until it gets closer might not be spotted until it's already within the orbit of Mars, giving us only a year or less. And this highlights why continued funding for sky surveys and planetary defense programs is so critically important. Every additional telescope scanning the skies, every improvement in detection algorithms and computational power, every advancement in our ability to characterize the orbits of potentially hazardous objects, increases our warning time and gives us a better chance of mounting an effective response if we ever do detect an incoming threat. In recent years, there's been growing interest in developing technologies that could potentially defend Earth against asteroid and comet impacts. NASA's DART mission, which successfully crashed a spacecraft into the asteroid Dimorphos in September 2022, demonstrated that it's possible to alter the trajectory of a small asteroid using kinetic impact, essentially hitting it hard enough to change its velocity. And while Dimorphos was only about 500 feet across, far smaller than a global threat class object, the mission proved the concept works and provided valuable data about how asteroids respond to impacts. But deflecting a comet is a much more challenging problem than deflecting an asteroid. Comets are often structurally weaker than asteroids because they're made of loosely consolidated ice and dust rather than solid rock, which means they might fragment if you hit them too hard, potentially turning one large threat into many smaller but still dangerous pieces. And comets move much faster than asteroids, which makes intercepting them more difficult and means you need to impart a larger velocity change to achieve the same deflection. And long-period comets from the Oort Cloud are especially problematic because we might not detect them until they're already close, leaving very little time to launch an interceptor mission, design and build a spacecraft capable of reaching the comet, and execute the deflection maneuver. One proposed solution to the long-period comet threat is to maintain a fleet of interceptor spacecraft in Earth orbit or at strategic locations in the solar system, ready to launch at a moment's notice. If a dangerous object is detected, these spacecraft would be equipped with propulsion systems capable of reaching high velocities quickly, allowing them to intercept comets even with limited warning time. And they might carry multiple types of payloads: kinetic impactors for solid asteroids, explosive devices for fragmenting or deflecting more robust objects, or even nuclear warheads for the most extreme scenarios where nothing else would work. Though the use of nuclear weapons in space is currently banned by international treaty and would require significant diplomatic negotiations to authorize, but in the face of an extinction-level threat, it's likely that nations would set aside their differences and authorize whatever measures were necessary to protect the planet. The psychological aspect of the comet threat is worth considering as well. Throughout human history, comets have been viewed with a mixture of awe and terror, appearing in the sky without warning, and often interpreted as omens of disaster, plague, war, or the death of kings. And while we now understand what comets actually are and can predict their movements with mathematical precision, there's still something fundamentally unsettling about the idea of these ancient visitors from the edge of darkness, objects that have witnessed the entire history of human civilization and existed for billions of years before life even emerged on Earth, suddenly appearing in our skies and potentially threatening our existence. And if we ever did detect a large Oort Cloud comet on a collision course with Earth, the social and psychological impacts would be profound, even if we had years of warning and a credible plan to deflect it. The knowledge that our entire species faced potential extinction would fundamentally change human behavior and society in ways that are difficult to predict. Some people might respond with determined effort to support the deflection mission and prepare for the worst. Others might descend into nihilism or hedonism, believing the end was inevitable, and there would undoubtedly be conflicts over resources and access to whatever safe havens or survival preparations were being made. The study of past impact events can tell us something about what to expect from future comet impacts. The Chicxulub crater in Mexico, that marks the dinosaur-killing impact, is 112 miles in diameter, suggesting the impactor was somewhere around 6 to 9 miles across, and geological studies of the impact site have revealed incredible details about what happened during and after the collision. The impact vaporized the rock beneath it and created a cloud of superheated material that rose into the atmosphere and fell back as molten droplets that ignited global fires. Sulfur-bearing rocks in the impact site were vaporized and converted to sulfuric acid, aerosols that spread through the stratosphere and blocked sunlight for years, causing a severe impact winter. And the evidence shows that the food chain collapsed within months, with large animals unable to find enough food in the perpetual twilight and cold. And it took tens of thousands of years for ecosystems to begin recovering, and millions of years for biodiversity to return to pre-impact levels. There have been other proposals for dealing with the comet threat that border on science fiction, but might be worth considering if we ever face a real emergency. One idea is to paint or coat an approaching comet with reflective material that would increase the pressure from sunlight hitting the surface, a phenomenon called radiation pressure, and over time this could gently push the comet off course without fragmenting it. Though the amount of material required to coat even a small comet would be enormous, and delivering it would require multiple spacecraft and years of advance warning. Another concept involves attaching a mass driver or ion engine to the comet's surface that would slowly but continuously apply thrust over months or years, changing the comet's trajectory through accumulated velocity changes. And while this sounds more feasible than coating the entire surface, landing a spacecraft on an active comet that's venting gas and dust would be incredibly difficult, as demonstrated by the European Space Agency's Rosetta mission, which successfully landed the Philae probe on Comet 67P Churyumov-Gerasimenko in November 2014. Though the landing didn't go quite as planned, with the probe bouncing and ending up in a shadowed area where its solar panels couldn't generate enough power. The question of whether Bernardinelli-Bernstein's carbon monoxide jets could alter its trajectory is actually an interesting one. From a physics perspective, when gas escapes from a comet's surface, it carries momentum, and by Newton's third law, the comet experiences an equal and opposite force, creating what's called a non-gravitational force that can slightly alter the orbital path over time. And for small comets, this effect can be significant enough to make predictions difficult, because you have to model not just the gravitational influences, but also how the outgassing varies with distance from the Sun and with the comet's rotation. But for something as massive as Bernardinelli-Bernstein, weighing approximately 500 trillion tons, the forces from carbon monoxide jets are utterly negligible. Like trying to change the course of a cruise ship by throwing tennis balls off the deck, the jets might produce thousands of tons of thrust collectively, which sounds impressive until you divide it by the comet's mass and realize the resulting acceleration is measured in millionths of a meter per second squared. So over the course of years or even decades, the jets will produce essentially no measurable change in the trajectory, and certainly nothing that could redirect the comet from its current safe orbit toward Earth. Ultimately, the threat posed by Oort Cloud comets, like Bernardinelli-Bernstein, is real but manageable if we take it seriously and invest in the technologies and infrastructure needed to detect and respond to these objects. The key is maintaining and expanding sky survey programs that can spot comets while they're still distant, improving our understanding of comet composition and structure so we can design effective deflection strategies, developing and testing deflection technologies through missions like DART, and maintaining international cooperation on planetary defense, because an impact anywhere affects everyone everywhere. And while the probability of a catastrophic comet impact occurring in any given year is extremely low, over the span of centuries and millennia, it becomes a near certainty that Earth will face this threat again, and whether human civilization survives that encounter may depend on the preparations we make today, the investments we choose to make in science and technology, and our ability to work together as a species to confront an existential threat that transcends national boundaries and political divisions, because ultimately, we all share this small blue planet, and protecting it from cosmic threats is one of the few challenges that truly affects all of humanity equally, regardless of race, religion, nationality, or any other division we create among ourselves. In 1977, when disco dominated the airwaves and the Cold War still gripped the world, NASA launched 2 identical spacecraft on what was supposed to be a simple 4-year mission to study Jupiter and Saturn. But those 2 probes, Voyager 1 and Voyager 2, would exceed every expectation and become humanity's most distant ambassadors, traveling farther from home than any object humans have ever created. And now, nearly 5 decades later, they're still out there, still transmitting data back to Earth from the void beyond the planets, from a realm no human has ever witnessed firsthand, sending us messages from the edge of everything we know about our cosmic neighborhood. The timing of the Voyager launches was crucial because it took advantage of a rare planetary alignment that occurs only once every 175 years, when the giant planets line up in such a way that a spacecraft can use gravitational assists from each planet to slingshot to the next one, dramatically reducing the travel time and fuel requirements needed to tour the outer solar system. And NASA seized this opportunity with both hands, designing the Voyager missions to take advantage of this cosmic gift and visit as many worlds as possible in a single grand tour. Voyager 2 actually launched first on August 20th, 1977, followed by Voyager 1 on September 5th, but Voyager 1 was placed on a faster trajectory that allowed it to overtake its twin and reach Jupiter first in March 1979. And what these spacecraft discovered during their planetary encounters revolutionized our understanding of the outer solar system. They found active volcanoes on Jupiter's moon Io, the first volcanic activity ever observed beyond Earth. They revealed Europa's cracked ice surface, suggesting a subsurface ocean that might harbor life. They captured stunning images of Saturn's intricate ring system, showing that what appeared through telescopes as a few broad rings were actually hundreds of narrow ringlets. They discovered new moons around Jupiter and Saturn, and they gave us our first close-up views of Uranus and Neptune, worlds so distant that even through our most powerful telescopes, they appeared as little more than fuzzy blue-green dots. But the planetary encounters, as spectacular as they were, turned out to be just the opening act, because after Voyager 1's close flyby of Saturn's moon Titan in November 1980, the spacecraft was flung upward out of the plane of the solar system by Saturn's gravity, sent on a trajectory that would take it away from the planets and toward the edge of the sun's influence. And Voyager 2, after completing its own tour that included Uranus in 1986 and Neptune in 1989, was also sent on an outbound trajectory into deep space, and both probes began what would become known as the Voyager Interstellar Mission, an extended mission to explore the outer reaches of the sun's domain and eventually cross into interstellar space. The journey to the edge was long, and for the most part uneventful. The spacecraft spent years coasting through the darkness beyond the planets, gradually moving farther from the sun. And during this time, NASA shut down most of their instruments to conserve power. The cameras that had captured those iconic images of Jupiter's Great Red Spot and Saturn's rings were permanently turned off on February 14, 1990, after Voyager 1 turned its camera back toward the inner solar system one last time and captured what would become known as the pale blue dot, an image showing Earth as a tiny speck of light suspended in a sunbeam, barely visible against the vastness of space. And that image, that humbling perspective of our world as an insignificant mote in an ocean of darkness, became one of the most profound photographs ever taken, inspiring Carl Sagan's famous reflection on humanity's place in the cosmos. As the Voyagers continued their outward journey, they were studying the environment around them with the instruments that remained active: magnetometers, measuring magnetic fields, plasma wave detectors, listening for electromagnetic waves, cosmic ray instruments, counting high-energy particles, and charged particle detectors, analyzing the composition and energy of the solar wind. And what they were looking for was the boundary, the edge of the heliosphere, where the sun's influence ends and interstellar space begins, a region that had never been directly explored and whose properties were largely unknown, predicted by theory, but never confirmed by observation. The heliosphere is a vast bubble inflated by the solar wind, that constant stream of charged particles flowing outward from the sun in all directions at speeds of about 1,000,000 miles per hour. And this wind pushes outward against the interstellar medium, the diffuse gas and dust that fills the space between stars, creating a boundary where the two meet and interact. And scientists predicted that this boundary, called the heliopause, would be somewhere around 10 to 15 billion miles from the sun, but nobody knew for sure because no spacecraft had ever been there to measure it. On August 25, 2012, after 35 years of traveling, Voyager 1's instruments detected a sudden and dramatic change in its environment. The rate of solar wind particles that had been streaming past the spacecraft for decades suddenly dropped to almost zero, while at the same time, the rate of galactic cosmic rays, high-energy particles coming from outside the solar system, suddenly increased. And after careful analysis of the data, NASA announced that Voyager 1 had crossed the heliopause and entered interstellar space, becoming the first human-made object ever to leave the solar system's protective bubble. And it was now sailing through a realm where the sun's influence had effectively ended and interstellar radiation dominated. Voyager 2 followed suit on November 5, 2018, crossing the heliopause at a different location because it took a different trajectory. And the fact that both spacecraft successfully made this crossing and sent back detailed measurements of the boundary has been invaluable for understanding the structure and dynamics of the heliosphere, revealing that the boundary is not smooth and static, but rather turbulent and constantly moving, buffeted by changes in the solar wind pressure and by the varying pressure of the interstellar medium pushing back from outside. What the Voyagers discovered about the heliopause contradicted many of the predictions that had been made. Scientists expected to find a gradual transition zone where solar winds slowly weakened and interstellar particles slowly increased. But instead they found a relatively sharp boundary. The solar wind didn't fade away. It hit a wall and essentially stopped. And beyond that wall, the environment was completely different, dominated by particles and magnetic fields from interstellar space rather than from the sun. And the temperature and density measurements taken by the spacecraft showed values that were 10 times different from what theoretical models had predicted, indicating that our understanding of the physics governing these interactions was incomplete. One of the most fascinating discoveries made by Voyager 1 in interstellar space was the detection of a persistent plasma oscillation, essentially a hum or vibration in the interstellar medium at a frequency of about 3 kilohertz, and this signal remained remarkably stable for nearly 3 years, suggesting that there's some source of energy in interstellar space that's driving these oscillations, something scientists hadn't predicted and still don't fully understand. And the only way they could detect this signal was because Voyager 1 was actually there, immersed in the interstellar medium with its plasma wave instrument functioning, recording these faint electromagnetic oscillations that no Earth-based telescope could ever detect. The spacecraft themselves are marvels of 1970s engineering that have far outlasted their original design life. Each Voyager is about the size of a small car, weighing roughly 1,700 pounds, and they're powered by radioisotope thermoelectric generators, or RTGs, which convert heat from the natural decay of plutonium-238 into electricity. And when they launched, these RTGs produced about 470 watts of power, enough to run a few household light bulbs. But over the decades, the plutonium has decayed, and the power output has steadily decreased, dropping by about 4 watts per year. And as of 2025, the spacecraft are generating less than 250 watts each, barely enough to power their remaining instruments and transmitters. The power crisis has forced NASA to make difficult decisions about which systems to keep running and which to shut down. Over the years, they've turned off heaters that kept various components warm, gambling that the electronics would continue functioning even at temperatures far below what they were designed for. And remarkably, many systems have survived these freezing temperatures and continued working, but not all. Some instruments have failed due to the cold or simply due to age, and the mission team has had to prioritize, keeping the instruments that are most valuable for studying interstellar space while reluctantly shutting down others to conserve power. In February 2025, NASA powered down Voyager 1's cosmic ray subsystem to save power, and similar shutdowns are planned for other instruments in the coming years. And current projections suggest that by sometime between 2025 and 2030, the spacecraft will no longer have enough power to operate even a single scientific instrument. And after 2036, they won't have enough power to run their transmitters, at which point they'll fall silent and will lose contact with them forever. But even after they go silent, the Voyagers will continue their journey through space, coasting on the velocity they built up during their planetary encounters, moving at about 38,000 miles per hour for Voyager 1 and 34,000 miles per hour for Voyager 2, and they'll drift through the galaxy for millions or billions of years, long after human civilization has either evolved into something unrecognizable or ceased to exist entirely. The distance the Voyagers have traveled is almost incomprehensible. As of October 2025, Voyager 1 is approximately 15.4 billion miles from Earth, which is about 165 times farther from the Sun than Earth is, and the radio signals it sends back, traveling at the speed of light, take over 23 hours to reach Earth, which means when mission controllers send a command to the spacecraft, they have to wait almost a full day for that command to arrive, and then another 23 hours for the spacecraft's response to travel back. So there's a 46-hour round-trip communication delay, making real-time control impossible, and this delay will only increase as the spacecraft continue moving away. In November 2026, Voyager 1 will reach a distance of 1 light day from Earth, meaning signals will take exactly 24 hours each way, and eventually the distances will become so great and the signals so weak that even NASA's most powerful antennas won't be able to detect them anymore. The ground-based infrastructure needed to communicate with the Voyagers is just as remarkable as the spacecraft themselves. NASA's Deep Space Network, or DSN, consists of 3 massive radio antenna complexes located roughly 120 degrees apart around Earth, one in California's Mojave Desert, one in Spain, and one near Canberra, Australia. And this global arrangement ensures that at least one station always has a view of the Voyagers as Earth rotates, allowing continuous communication. And the largest antennas in the DSN, the 70-meter dishes, are so sensitive that they can detect signals from Voyager 1 that arrive at Earth with a power of only about 1/1000th of a watt. That's less energy than it takes for a snowflake to hit the ground. And yet these massive dishes can pluck that faint whisper out of the cosmic noise and decode it into meaningful scientific data. The Voyagers have faced numerous technical challenges over the decades that could have ended their missions. Thruster tubes have become clogged with debris, forcing engineers to switch to backup systems, or even revive thrusters that hadn't been used in decades. In December 2017, NASA successfully fired Voyager 1's trajectory correction thrusters for the first time since 1980, and these thrusters, which had been dormant for 37 years, worked perfectly, allowing the mission to continue for several more years. And in May 2025, engineers performed another near miracle by reviving backup roll thrusters on Voyager, one that had been inoperative since 2004, breathing new life into the aging spacecraft. In November 2023, Voyager 1 suddenly fell silent, transmitting only meaningless streams of binary data, instead of coherent information. And after months of troubleshooting across the 23-hour communication delay, engineers determined that a memory chip in the spacecraft's flight data system had failed. And they made the bold decision to relocate the corrupted code to other areas of the spacecraft's memory, essentially performing surgery on a computer from 15 billion miles away using 47-year-old technology. And the operation began on April 18, 2024, with each command taking over 22 hours to reach the spacecraft and responses taking another 22 hours to return. So the team had to wait almost 2 days to find out if each step had worked. And incredibly, on April 20th, they confirmed success. Voyager 1 was restored to full health and resumed transmitting science data. And this remarkable rescue demonstrated both the ingenuity of the mission team and the robustness of the spacecraft's design. The Voyagers carry messages for any extraterrestrial intelligence that might someday encounter them. Each spacecraft includes a golden record, a 12-inch gold-plated copper disc containing sounds and images selected to portray the diversity of life and culture on Earth. The records include greetings in 55 languages, music from various cultures and eras, including Bach, Mozart, Chuck Berry, and traditional songs from around the world, natural sounds like thunder, waves, birds, and whales, and 116 images showing mathematical definitions, human anatomy, animals, landscapes, and scenes of human civilization. And there's even a recorded message from President Jimmy Carter and a diagram showing Earth's location relative to 14 pulsars, cosmic lighthouses, whose precise periods could allow an advanced civilization to determine when and where the records came from. The trajectory of Voyager 1 is carrying it toward the constellation Ophiuchus, and in about 40,000 years, it will pass within about 1.7 light-years of a dim star called Gliese 445, and Voyager 2 is headed toward the constellation Andromeda and will pass within about 1.7 light-years of a star called Ross 248 in roughly 40,000 years. But these are just the first of countless stars the Voyagers will silently drift past over the eons. And while the chances of either spacecraft actually being found by an alien civilization are infinitesimally small, the golden records represent a message in a bottle cast into the cosmic ocean, a statement that we existed, that we were here, that we created these machines and sent them out into the universe as ambassadors of our species. Even though the Voyagers crossed the heliopause years ago, they're still nowhere near leaving the solar system in the fullest sense, because the sun's gravitational influence extends far beyond the heliopause, all the way out to the Oort Cloud, that vast spherical shell of icy debris that surrounds our entire planetary system. And the inner edge of the Oort Cloud is thought to begin at around 2,000 astronomical units from the Sun, while Voyager 1 is currently only about 165 astronomical units out, which means it will take roughly 300 more years to reach the inner edge of the Oort Cloud, and another 30,000 years to traverse it completely and finally exit the region where the Sun's gravity dominates. So while the Voyagers have left the heliosphere and entered interstellar space in terms of the particle environment, they're still gravitationally bound to the solar system and will be for millennia to come. The legacy of the Voyager missions extends far beyond the scientific discoveries they've made. They've inspired generations of scientists and engineers, demonstrated what's possible when we commit to long-term exploration, and provided a template for how to operate spacecraft across vast distances with limited resources and aging hardware. The mission has taught us about designing systems that can last for decades, about managing power budgets when every watt counts, about troubleshooting complex problems across communication delays measured in days, and about maintaining the institutional knowledge needed to operate spacecraft when the original designers and engineers have retired or passed away and new generations have taken over. The data the Voyagers have returned about the structure of the heliosphere and the nature of interstellar space has challenged our theoretical models and forced us to rethink our understanding of how the Sun interacts with its galactic environment. They've shown us that the boundary between solar and interstellar space is dynamic and complex, shaped by processes we're only beginning to understand. And they've given us our first direct measurements of the density, temperature, and magnetic field strength of the local interstellar medium, the neighborhood of space that our solar system is currently passing through as it orbits the galactic center. As the Voyagers continue their journey and gradually fall silent over the next decade or so, they'll leave behind a scientific legacy that few missions can match. They've operated for nearly 50 years, far longer than anyone expected. They've traveled farther than any other human-made objects. They've visited 4 planets and dozens of moons. They've crossed into interstellar space and sent back data from that unexplored frontier. And they've shown us that with careful engineering, smart management, and a bit of luck, spacecraft can continue functioning long after their original mission ends, opening up possibilities for exploration that would have seemed impossible when they launched. And perhaps most importantly, they've given us a new perspective on our place in the universe, showing us that we're not confined to Earth or even to our solar system, that we can reach out into the cosmos and touch the space between the stars. And while the Voyagers themselves will eventually go silent and drift through the galaxy as dead hulks, the knowledge they've returned and the inspiration they've provided will continue shaping human exploration of space for generations to come, reminding us that we're capable of remarkable things when we dare to venture into the unknown and confront the vast darkness that lies beyond our small blue world. Our solar system exists inside not just one protective bubble, but 2 nested shields that have been safeguarding life on Earth for millions of years. And understanding these barriers, how they formed, and what they do, reveals just how fortunate we are to exist in this particular location, in space, at this particular moment in galactic history. Because without these dual layers of protection, the surface of Earth would be constantly bombarded by lethal cosmic radiation that would make the evolution of complex life virtually impossible. And the fact that both of these bubbles exist simultaneously is not just coincidence, but the result of specific conditions and violent events that happened long before humans existed, and long before dinosaurs walked the Earth. The first bubble, the one closest to us and most directly tied to the Sun, is called the heliosphere, and it's created by the solar wind, that constant stream of charged particles, primarily protons and electrons, that flows outward from the Sun in all directions at speeds of about 1 million miles per hour. And this wind isn't just a gentle breeze, it's a supersonic plasma flow, carrying with it the Sun's magnetic field. And as it pushes outward, it creates a vast bubble that extends for billions of miles in all directions, carving out a region of space dominated by solar particles and solar magnetic fields. And the edge of this bubble, where the solar wind finally slows down and stops as it crashes into the interstellar medium, is called the heliopause. And both Voyager spacecraft have now crossed this boundary and are sending back data from beyond it. The heliosphere extends roughly 11 billion miles from the Sun, which sounds enormous until you remember that the Oort Cloud extends potentially 2 light-years out. But within that 11 billion mile radius, the solar wind is flowing outward fast enough to push back against the interstellar medium, creating a protective cocoon around all the planets. And this protection is crucial because space is filled with galactic cosmic rays, high-energy particles accelerated to nearly the speed of light by supernovae and other violent cosmic events. And these particles are so energetic that they can damage DNA, destroy electronic systems, and make space travel extremely hazardous. But the heliosphere deflects or slows down many of these particles, reducing the radiation dose that reaches the inner solar system where Earth orbits. And studies suggest that without the heliosphere, the cosmic ray flux at Earth's orbit could be 10 to 100 times higher than it currently is, which would have profound effects on atmospheric chemistry, climate, and the evolution of life. The structure of the heliosphere is more complex than just a simple sphere. The sun is moving through the galaxy at about 43,000 miles per hour, relative to the local interstellar medium, and this motion creates an asymmetry in the heliosphere, compressing it in the direction of motion and stretching it out behind into a long tail called the heliotail, similar to how a comet develops a tail as it moves through space. And the Voyager spacecraft crossed the heliopause at different distances. Voyager 1 at about 122 astronomical units, and Voyager 2 at about 119 astronomical units. And this difference tells us that the heliosphere's shape and size vary depending on direction and are influenced by the changing pressure of the solar wind and the varying density of the interstellar medium that the sun is currently moving through. But the heliosphere is just the inner bubble, the first line of defense, and surrounding our entire solar system at a much larger scale is a second bubble called the local bubble, and this structure is absolutely enormous, measuring approximately 1,000 light-years in diameter, which means light takes 1,000 years to cross from one side to the other, and we're sitting almost exactly at the center of this vast void. And unlike the heliosphere, which is created by our sun, the local bubble was carved out by something far more violent, a series of supernova explosions that occurred between 10 million and 14 million years ago. Supernovae are among the most powerful events in the universe, when a massive star exhausts its nuclear fuel and can no longer support itself against gravity. The core collapses in a fraction of a second and then rebounds in a catastrophic explosion that releases more energy in a few seconds than the sun will produce over its entire 10 billion year lifetime. And the explosion hurls the star's outer layers into space at speeds of tens of thousands of miles per second, creating an expanding shock wave that plows through the interstellar medium, sweeping up gas and dust and pushing it outward. And when multiple supernovae explode in the same region over a period of several million years, their shock waves interact and merge, creating enormous bubbles in the interstellar medium, with dense walls of compressed gas at the boundaries and relatively empty interiors. This is exactly what happened in our region of the galaxy. About 14 million years ago, astronomers using data from the European Space Agency's Gaia spacecraft, which has measured the precise positions and motions of over 1 billion stars, were able to create a three-dimensional map of the space around the sun. And what they discovered was stunning. We're sitting inside a nearly perfect sphere of empty space, a void where the density of interstellar gas is about 1/10 of what it is in surrounding regions. And on the surface of this bubble, at distances of about 500 light-years in various directions, are 7 distinct star-forming regions, where dense clouds of molecular gas are collapsing to form new stars. And these regions include famous stellar nurseries like the Taurus molecular cloud and the Ophiuchus cloud. The researchers ran sophisticated computer simulations, going backwards in time, to figure out when and how this bubble formed, and their models showed that approximately 15 supernovae would need to have exploded in this region between about 14 million and 10 million years ago to create a bubble of this size. And these explosions weren't random events in unrelated parts of the galaxy. They were all part of the same stellar population, massive stars that formed together from the same giant molecular cloud and then exploded in sequence as they exhausted their fuel, with the most massive stars exploding first and the slightly less massive ones following over the next few million years. And each explosion added energy to the expanding bubble, keeping it growing and pushing the walls of compressed gas farther outward. What makes this discovery even more remarkable is that the sun wasn't always inside the local bubble. When these supernovae started exploding 14 million years ago, our sun was about 1,000 light-years away from the scene. But the sun orbits around the center of the Milky Way galaxy, just like all the other stars. and it takes about 225 million years to complete one orbit. And as it moves through space, it passes through different regions with different properties, sometimes traveling through the dense spiral arms of the galaxy, where star formation is active and interstellar gas is abundant, and sometimes cruising through the quieter spaces between the arms. And about 5 million years ago, purely by chance, the Sun's galactic orbit carried it into the interior of the local bubble, and we've been inside ever since, enjoying the protection and the clear views that this void provides. The interior of the local bubble isn't completely empty. There's still some gas there, but the density is only about 0.005 atoms per cubic centimeter, compared to about 0.5 atoms per cubic centimeter in the surrounding interstellar medium, making it about 100 times less dense than the space outside the bubble. And the gas that remains inside the bubble is extremely hot, about 1 million degrees Kelvin, which sounds dangerous, but is actually not a threat because the density is so low that there's not enough material there to transfer significant heat to anything. It's like the difference between sticking your hand in a conventional oven at 400 degrees Fahrenheit, which will burn you quickly, and sticking your hand in a room full of 400-degree air at very low pressure, where you'd barely feel the warmth, because there aren't enough air molecules hitting your skin to transfer heat efficiently. The local bubble's walls, where all that swept-up material accumulated, are extremely dense by interstellar standards, with densities 10 to 100 times higher than average. And it's in these compressed walls that new stars are forming, because when you squeeze interstellar gas, you increase its density, and if the density gets high enough, gravity takes over, and the gas begins collapsing into clumps that eventually become stars. So ironically, the violent deaths of massive stars and supernova explosions trigger the birth of new generations of stars on the edges of the bubbles they create. And this process of stellar death and rebirth is one of the fundamental cycles that drives the evolution of galaxies. The existence of the local bubble has implications for life on Earth that scientists are only beginning to understand. High-energy cosmic rays, particularly those accelerated by supernova remnants, can have significant effects on planetary atmospheres and on the chemistry of life. And when the supernovae that created the local bubble were exploding, they would have dramatically increased the cosmic ray flux throughout this region of space, and some of those cosmic rays would have reached Earth, potentially affecting the atmosphere, the climate, and even the mutation rates of organisms. And there's been speculation that increased cosmic ray bombardment during periods of intense supernova activity might have contributed to some of the mass extinction events in Earth's history, though proving such connections is extremely difficult because the geological and fossil records from millions of years ago are incomplete, and the timing of supernovae is uncertain. The fact that we're now inside the bubble, protected from some of that external radiation, is potentially beneficial for life. The interior of the local bubble is shielded to some degree from the most intense cosmic ray sources in the surrounding galaxy, and this might reduce the background radiation level slightly, though the effect is probably modest because cosmic rays can travel long distances and aren't completely blocked by the bubble walls. But every little bit of protection helps when you're trying to maintain a stable environment for complex life to evolve over billions of years. The local bubble is also not unique. The Milky Way galaxy is filled with similar structures. Astronomers have identified hundreds of bubbles and superbubbles created by past supernova explosions, and these structures give the interstellar medium a frothy Swiss cheese-like texture with dense walls surrounding relatively empty voids, and stars move through this complex landscape as they orbit the galaxy, sometimes finding themselves inside bubbles, and sometimes outside, sometimes passing through the dense walls where star formation is active, and each environment exposes the star and its planets to different conditions, different radiation levels, different densities of interstellar material. And over the billions of years that a star like the Sun exists, it will pass through many different environments, and the history of life on Earth has been shaped by all of these changing conditions. The dual bubble structure, The heliosphere nested inside the local bubble provides a layered defense system. The heliosphere primarily protects against charged particles, using the sun's magnetic field embedded in the solar wind to deflect or scatter incoming cosmic rays and interstellar particles. And this protection is most effective against lower energy particles, while very high energy cosmic rays can penetrate the heliosphere more easily. But even high energy particles are slowed down, and their trajectories are bent by the magnetic fields in the heliosphere, reducing the flux that reaches the inner solar system. And the local bubble provides a different kind of protection by simply removing much of the dense interstellar material that could otherwise interact with the heliosphere and compress it or disrupt it, and by keeping us away from the most intense sources of cosmic rays in nearby star-forming regions, where massive stars are exploding. Scientists studying Earth's past climate and the evolution of life have found intriguing correlations between the sun's journey through different galactic environments and major events in Earth's history. There's evidence suggesting that when the solar system passes through the dense spiral arms of the Milky Way, where star formation is active and supernova rates are higher, Earth experiences increased cosmic ray bombardment. And some researchers have proposed that this could trigger ice ages by increasing cloud formation in the atmosphere, because cosmic rays can ionize air molecules and create charged particles that serve as nucleation sites for water vapor to condense into cloud droplets. And more clouds means more sunlight reflected back to space, leading to cooling, though this hypothesis remains controversial and the connections are difficult to prove definitively. There have also been attempts to correlate the timing of mass extinction events with the solar system's position in the galaxy. The idea being that passing through a spiral arm or encountering a nearby supernova could increase radiation levels enough to cause significant damage to the ozone layer, allowing harmful ultraviolet radiation from the sun to reach the surface, or could increase mutation rates in organisms leading to cancer and reproductive problems. And while some correlations have been found, the uncertainties in dating both the geological events and the galactic positions make it hard to establish clear cause and effect relationships. But the fact that such correlations exist at all is suggestive and motivates continued research into how our galactic environment influences conditions on Earth. The heliosphere itself varies in size and strength over time, not just over millions of years, as the sun moves through different interstellar environments, but also on much shorter timescales related to the solar cycle. The sun goes through an approximately 11-year cycle of activity, where the number of sunspots, solar flares, and coronal mass ejections waxes and wanes. And during solar maximum, when activity is high, the solar wind is stronger and more variable, pushing the heliopause farther out. And during solar minimum, when the sun is quiet, the solar wind weakens and the heliopause moves inward. And these variations can change the size of the heliosphere by 10 to 20% or more, affecting how much cosmic radiation reaches the inner solar system. NASA and other space agencies are intensely interested in understanding the heliosphere better because it directly affects the safety of astronauts. When humans eventually travel to Mars or establish bases on the Moon, they'll be exposed to much higher levels of cosmic radiation than we experience on Earth's surface, where the atmosphere and magnetic field provide additional protection. And accurately predicting the radiation environment in space requires detailed models of how the heliosphere works, how it responds to changes in solar activity, and how cosmic rays propagate through it. And the data from Voyager 1 and 2 has been invaluable for testing and improving these models, showing that the actual structure is far more complex than the simple spherical bubble that early theories predicted. The discovery that we're living inside the local bubble also has implications for astronomy and our ability to observe the universe. One reason we can see so many stars and have such clear views of distant galaxies is precisely because we're inside a void with very little interstellar dust to block our view. If we were in a denser region of the galaxy, much of the visible light and ultraviolet radiation from distant objects would be absorbed by dust grains before reaching us, limiting what we could see with our telescopes. So in a very real sense, the local bubble has enabled human astronomy by providing us with a privileged viewing location, and this is one more way in which our circumstances seem almost designed for the development of an intelligent technological civilization. Though whether this is just luck or represents some kind of deeper principle remains a matter of philosophical debate. As the Sun continues its orbit around the galaxy, it will eventually exit the local bubble, probably in a few million years. And when that happens, conditions in the solar system will change. The density of interstellar gas will increase, putting more pressure on the heliosphere and potentially compressing it to a smaller size. And this could allow more cosmic radiation to reach the inner solar system, affecting Earth's climate and potentially posing challenges for any future human civilization that is spread throughout the solar system, but on the timescale of millions of years. Humanity will either have evolved into something unrecognizable, develop technologies to protect against such threats, or cease to exist. So while it's interesting to contemplate these future changes, they're not an immediate concern. The dual bubble structure surrounding our solar system is a reminder that Earth is not isolated from the cosmos, but is embedded in a complex and dynamic galactic environment that has shaped our planet's history and continues to influence conditions today. From the solar wind blowing outward from our star to the ancient supernova explosions that carved out the void we're floating through. These cosmic forces are always at work, sometimes protecting us, sometimes threatening us, but always connecting our small world to the larger universe. And understanding these connections is not just an academic exercise, but a practical necessity as humanity ventures beyond Earth and confronts the realities of living in space. Because once we leave the protective cocoon of Earth's atmosphere and magnetic field, we'll be directly exposed to these cosmic influences, and our survival will depend on our ability to predict, understand, and mitigate the hazards that come from living in an active and sometimes violent universe. Beyond the heliopause, beyond the Oort Cloud, beyond everything that we consider, part of our solar system lies true interstellar space, the vast ocean of darkness between the stars. And this is where the Voyagers are now, the first human-made objects to venture into this alien realm, sending back their faint whispers about what they're finding. But they're moving incredibly slowly by interstellar standards, covering about 3.5 astronomical units per year, which sounds fast until you realize that the nearest star system, Alpha Centauri, is over 4 light years away, or about 270,000 astronomical units, which means even at Voyager 1's current speed, it would take over 70,000 years to reach that nearest stellar neighbor. And that's if it were actually heading in that direction, which it's not. Instead, it's pointed toward a dim star in the constellation Ophiuchus that it won't reach for another 40,000 years. And this raises the fundamental question that has haunted humanity since we first looked up at the night sky and wondered about those distant points of light. Will we ever actually travel to the stars? Will human beings or our descendants or the machines we create ever cross the interstellar void and visit other solar systems? Or are we forever confined to this one tiny corner of the galaxy, limited by the laws of physics that seem to make interstellar travel impossibly difficult? The distances involved in interstellar travel are so vast that they defy human comprehension. We talk about light years as if they're just another unit of measurement, but a light year is the distance light travels in 1 year, moving at 186,000 miles per second, never slowing, never stopping, and that works out to about 6 trillion miles, and the nearest star is over 4 of those light years away, roughly 25 trillion miles, which is 6,000 times farther than the distance from the Sun to Pluto. And the galaxy is 100,000 light years across, and the universe extends for billions of light years in all directions. And when you truly grasp these scales, the challenge of interstellar travel becomes painfully clear. we're not just talking about going farther than we've gone before. We're talking about increasing travel distances by factors of thousands or millions compared to anything humanity has ever attempted. The energy requirements for interstellar travel are equally staggering. If you want to send even a small spacecraft to another star system in a reasonable amount of time, say 50 or 100 years, you need to accelerate it to a significant fraction of the speed of light, maybe 10 or 20% of light speed. And the kinetic energy involved in accelerating even a tiny 1-ton payload to 10% of light speed is roughly 450 petajoules, which is about 125 terawatt-hours, comparable to a significant fraction of the entire world's annual energy production. And that's just the energy needed to accelerate the payload. It doesn't include the energy needed to accelerate the fuel, or the inefficiencies of whatever propulsion system you're using, or the energy needed to decelerate when you arrive at your destination. If you want to do anything other than flash past at enormous speed, and when you account for all of those factors, the total energy requirements become truly astronomical, possibly requiring more energy than human civilization currently produces in years or decades. One of the most serious hazards facing any interstellar spacecraft traveling at a significant fraction of light speed is the interstellar medium itself, the diffuse gas and dust that fills the space between stars. In the region around our Sun, the density of the interstellar medium is about 0.2 atoms per cubic centimeter, which sounds like nothing, and by everyday standards it is nothing. It's a far better vacuum than anything we can create in laboratories on Earth. But when you're moving at 10 or 20% of light speed, even these sparse atoms become deadly projectiles, because kinetic energy scales with the square of velocity. A hydrogen atom hitting your spacecraft at 20% of light speed carries as much energy as a bullet. And there are millions of these atomic bullets hitting every square centimeter of your spacecraft's surface every second, gradually eroding any material and potentially causing catastrophic damage. And larger particles, dust grains even a fraction of a millimeter across, would impact with the force of bombs, punching through hulls and destroying equipment. And there's no easy way to shield against this, because any shield massive enough to stop these impacts would be too heavy to accelerate to the required speeds in the first place. Various solutions have been proposed to deal with the interstellar medium problem. One idea is to use a powerful magnetic field projected in front of the spacecraft to deflect charged particles before they can hit the hull, essentially creating an artificial magnetosphere, like Earth's, that would push incoming protons and electrons aside. But this requires enormous amounts of power to generate a magnetic field strong enough and large enough to be effective at relativistic speeds, and it wouldn't help with neutral particles like dust grains that aren't affected by magnetic fields. Another proposal involves placing a sacrificial shield in front of the spacecraft, essentially a thick slab of material designed to absorb impacts and slowly ablate away. But again, the mass requirements make this impractical for anything moving at a significant fraction of light speed. And some designs have proposed using clouds of plasma or small particles deployed ahead of the spacecraft to fragment or vaporize incoming dust before it reaches the main vehicle. But all of these solutions add complexity, mass, and power requirements to an already extremely challenging engineering problem. The concept of generation ships has been proposed as a way to bypass some of the energy requirements of high-speed travel. Instead of trying to reach relativistic velocities, you build a massive spacecraft that accelerates slowly to maybe 1 or 2% of light speed. And instead of trying to complete the journey in decades, you accept that it will take thousands of years, and you design the ship to be a completely self-contained ecosystem, capable of supporting a human population for hundreds of generations, with people being born, living their entire lives, and dying aboard the ship, and their children and grandchildren continuing the journey, until eventually, millennia later, the distant descendants of the original crew arrive at the destination star system And while this solves some problems, it creates others. Maintaining a viable human population with sufficient genetic diversity over thousands of years is challenging. Preventing genetic bottlenecks and inbreeding requires a minimum population of several hundred or perhaps several thousand people, all of whom need food, water, air, living space, and something to do for their entire lives. In maintaining all the life support systems and keeping the ship functioning for millennia without any possibility of resupply or external repair presents engineering challenges that may be even harder than the propulsion problem. And there are profound psychological and sociological questions about what it means to condemn dozens or hundreds of generations to live and die in a confined artificial environment, never seeing a planet, never experiencing the sky or oceans or forests, living only for a mission that was started by their distant ancestors and will only be completed by their distant descendants. Another approach that has gained attention in recent years is the concept of sending tiny lightweight probes rather than large crewed spacecraft. Projects like Breakthrough Starshot propose using powerful lasers based on Earth or in orbit to accelerate thousands of miniature spacecraft, each weighing only a few grams and equipped with a light sail. The laser would push on the sail, accelerating the probe to perhaps 20% of light speed over a period of minutes or hours. And because the probe is so small and light, the energy requirements, while still enormous, become at least theoretically achievable with foreseeable technology, and thousands of probes would be launched to ensure that at least some survive the journey through the interstellar medium and arrive at the target star system, where they would fly past, taking measurements and images for a few hours during their closest approach, and then spend years transmitting that data back to Earth using tiny onboard lasers. But even this scaled-down approach faces immense challenges. Building the laser array would cost billions or tens of billions of dollars. The probes would need to survive acceleration forces of tens of thousands of Gs without breaking. They would need to function for decades in the harsh environment of space, with no possibility of repair or maintenance. And the amount of data they could collect during a brief flyby would be limited. But at least this approach seems physically possible with technology that might be developed in the next few decades or century. The possibility of faster-than-light travel has been a staple of science fiction for over a century, with writers inventing warp drives, hyperspace, jump drives, and countless other mechanisms to bypass the light speed limit and make interstellar travel practical. But according to Einstein's theory of special relativity, which has been confirmed by countless experiments over the past century, nothing with mass can accelerate to or beyond the speed of light, because as you approach light speed, your mass effectively increases, requiring ever more energy to accelerate further, and at exactly light speed, your mass would become infinite, requiring infinite energy to accelerate, which is physically impossible. So the light barrier seems absolute, at least for ordinary matter and energy, but there are some theoretical loopholes in the laws of physics that might, and this is a very big might, allow for something resembling faster than light travel. One such loophole involves wormholes, theoretical tunnels through space-time that could connect two distant points, allowing you to travel between them without actually moving through the intervening space. Einstein's general theory of relativity, which describes gravity as the curvature of space-time, allows for the mathematical possibility of wormholes, but creating or maintaining a traversable wormhole would require something called exotic matter with negative energy density. And while quantum mechanics suggests that negative energy can exist in very small quantities in very specific circumstances, something called the Casimir effect, scaling this up to the amounts needed for a wormhole, if it's even possible, would require technology so far beyond our current capabilities that it's essentially magic, and there are serious questions about whether wormholes could even remain stable. Quantum effects might cause them to collapse instantly, or radiation might build up inside them to lethal levels, destroying anything trying to pass through. And even if somehow wormholes could be created and stabilized, you'd need two of them, one at each end of the journey, so you'd have to transport one end to your destination by conventional slower than light, means before you could use the wormhole for rapid travel, which defeats much of the purpose. Another theoretical possibility is the Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994, which involves warping space-time itself, contracting space in front of your spacecraft, and expanding it behind you so that you're essentially surfing on a wave of space-time. And because it's space itself that's moving, rather than your spacecraft moving through space, you could theoretically travel faster than light without violating relativity, at least in principle. But the energy requirements for this are truly absurd. Initial calculations suggested you'd need more energy than exists in the entire visible universe. Later refinements brought this down somewhat, but still require the mass energy equivalent of Jupiter or larger. And again, you'd need exotic matter with negative energy. And there are questions about whether such a warp bubble could even be created or controlled, and whether the people inside would be causally disconnected from the universe outside, unable to start or stop the bubble once it was in motion. So while the Alcubierre drive is a fascinating mathematical solution to Einstein's equations, it's probably not a practical method for interstellar travel, at least not with any technology we can currently imagine. The biological challenges of interstellar travel are just as daunting as the physics and engineering challenges. Humans did not evolve for life in space. We evolved under 1 g of gravity, breathing Earth's atmosphere, eating Earth's food, exposed to Earth's magnetic field and radiation environment. And when you take humans off Earth for extended periods, their bodies start to break down. Bones lose density because they're not bearing weight. Muscles atrophy. The cardiovascular system weakens because the heart doesn't have to work as hard to pump blood. Vision deteriorates due to fluid shifts in the skull. The immune system becomes compromised, and cosmic radiation damages DNA, increasing cancer risk. And all of these effects have been observed in astronauts who spent months on the International Space Station in low Earth orbit, where they're still partially protected by Earth's magnetic field. And the effects would be much worse on an interstellar journey, where travelers would be exposed to the full intensity of galactic cosmic radiation for years or decades or generations, with no planet nearby to provide protection. And while rotating the spacecraft to create artificial gravity could solve some of the bone and muscle problems, it doesn't help with radiation, and shielding against cosmic rays is extremely difficult because they're so energetic that conventional shielding just creates secondary radiation when the particles hit the shield material, fragmenting into showers of particles that might be just as dangerous as the original cosmic rays. Some have proposed that the solution to the biological challenges of interstellar travel is to not send biological humans at all. Instead, we could send frozen embryos or stored genetic material and artificial wombs that would create humans at the destination. Or we could send digital uploads of human consciousness stored in computers. Or we could send artificial intelligence that would explore on our behalf and report back what it finds. Or we could fundamentally modify human biology through genetic engineering or cybernetic enhancement to create beings better suited for life in space, able to tolerate radiation, able to hibernate for long periods, able to regenerate damage, essentially creating a new species of space, adapted humans or post-humans. But all of these solutions raise profound ethical questions about what it means to be human, and whether these modified or artificial beings would still represent humanity in any meaningful sense, and whether we have the right to create new conscious beings just to send them on a one-way trip into the void. Despite all these challenges, there are reasons to think that interstellar travel, while extraordinarily difficult, may not be impossible. Technology has advanced in ways that would have seemed like magic to people living centuries ago. We split the atom, we decoded the genome, we created computers, millions of times more powerful than the machines that sent people to the moon. And these advances happened in less than a century. So who knows what might be possible in 1,000 years, or 10,000 years, if human civilization continues to develop, and while faster than light travel still seems physically impossible, traveling at 10 or 20% of light speed, using advanced propulsion technologies like fusion rockets or antimatter engines, or laser-pushed light sails seems challenging, but not impossible. It's just extremely expensive and would require commitment and resources on a scale that no current nation, or even all nations combined, have been willing to invest in space exploration. But that could change if we discovered something really compelling at another star system, if we detected signs of life or even technological civilization on a planet around a nearby star. The political will and resources to mount an interstellar mission might suddenly materialize. The Voyager spacecraft, now over 15 billion miles from Earth and still functioning after nearly 50 years, demonstrate that we can build machines capable of surviving for decades in the harsh environment of deep space. And while they're moving far too slowly to reach another star in any reasonable time frame, they prove that long-duration missions are possible, and future probes could be faster, more robust, more capable, equipped with ion drives, or nuclear propulsion, or other advanced technologies that the Voyagers don't have. And if we're patient, if we're willing to think in terms of centuries rather than decades, we could send robotic missions to nearby stars that would arrive within the lifetime of our civilization, if not within the lifetime of any individual person. And these missions would send back data and images from truly alien worlds, planets orbiting other suns, potentially inhabited by life forms that evolved completely independently from anything on Earth. And that knowledge alone might be worth the cost and effort. The question of whether humanity will ever physically travel to the stars remains open. The physics says it's possible, but extremely difficult. The engineering challenges are immense, but perhaps not insurmountable. The biological challenges are severe, but might be solved through technology or modification. And the economic and political will to undertake such missions doesn't exist now, but could develop in the future if the right circumstances arise. And perhaps the answer is that we'll never send crewed missions to other star systems, at least not in the traditional sense, but we'll send increasingly sophisticated robots and AI that will explore on our behalf, and we'll send our knowledge and culture encoded in messages and databases. And in a sense, those missions will represent humanity among the stars, even if no biological humans are present. And maybe that's enough. Maybe the important thing is not that human bodies reach other stars, but that human knowledge and human creativity and human curiosity reach out into the cosmos, touching worlds that orbit alien suns, and asking the questions that have driven us since the first human looked up at the night sky and wondered what those lights in the darkness might be. And the Voyagers, those two small spacecraft launched in 1977, carrying their golden records with sounds and images from Earth, are the first tentative steps in that endless journey, ambassadors from a species that barely understands its own planet, but nevertheless dares to reach out toward the stars. And while they'll eventually fall silent and drift through the galaxy for billions of years, long after Earth and the Sun are gone, they'll remain as proof that we were here, that we existed, that we built these machines and sent them into the infinite darkness, not knowing if they would succeed or fail or ever be found, but sending them anyway because the urge to explore and to know and to reach beyond our grasp is fundamental to what makes us human. And as long as that urge exists, as long as there are people looking up at the stars and asking what if, there's hope that someday, somehow, whether in our current form or as something we can barely imagine, humanity or its descendants will find a way to cross the void and stand beneath alien skies, fulfilling the ancient dream of voyaging to the stars and making real what has been fantasy for so long, proving that the final frontier is not a barrier, but an invitation.